actually recording. There it is. So don't need my mobile number on Facebook or on YouTube. So chapter 13 begins with temperature. So just talking about the concept of temperature and what temperature means. And the biggest thing that messes up students for solving some of these problems is how to convert temperatures, right? So you have, and we'll get to this, equations like the ideal gas law, where pressure times volume is equal to the number of moles times the gas constant times temperature. Or you'll get something like the change in length is the original length times the coefficient of linear expansion times the change in temperature. Delta T and T are different things, right? Temperature always means absolute temperature, right? Temperature here in Kelvin. Always, always, always. So for the ideal gas law, that T, a temperature of 0 means absolute 0. So you cannot use Celsius, you cannot use Fahrenheit when dealing with these problems. The linear expansion equation, delta T, means change in temperature. That's trickier because if I give you a delta T, let's say I give you a delta T, which is equal to 100 Celsius degrees. And I ask you to convert that to what's delta T in Kelvin? Now, hopefully most of you noticed that it's a change in temperature, so 100 Celsius degrees is the same as a change in 100 Kelvin. You don't add 273.15 to it. If I want a temperature of 100 degrees Celsius is 373.15 Kelvin, but a temperature difference, the step size for Celsius degrees is the same as the step size for Kelvin. So that's something that you definitely want to keep in mind. Additionally, if I had to do this in Fahrenheit, or if I gave you the temperature difference in Fahrenheit, again, converting to Fahrenheit, temperature in Fahrenheit, take your temperature in degrees Celsius, multiply it by 5/9, and add 32 to it. But a temperature difference, you just multiply by 9/5. So that'd be 180 degrees Fahrenheit. Because this 32 is an offset because 0 degrees Celsius is 32 degrees Fahrenheit. The step sizes, for every 5 degrees Celsius, there's 9 degrees Fahrenheit in the same step size. So since we're dealing with temperature in these chapters, I just want to reinforce that that's a common mistake made in these problems. So when doing pressure, sorry we started a little bit early, people were done with labs, but if you have any questions, we'll circle back. So temperature, we just started. Temperature, chapter 13, don't forget to convert. Right? It's fairly safe to convert. You have to convert to Kelvin here, but Celsius degrees change in temperature or Kelvin change in temperature are the same. Questions on that at all? Yes.
So would you have to convert to Fahrenheit? Like say if it was given in Fahrenheit, you'd have to convert it to either Celsius or Kelvin from that?
Yes, so if I gave you delta T in Fahrenheit, then you would have to do the opposite. So delta T in Fahrenheit, delta T in degrees Fahrenheit is just, oh sorry, this is 9/5, not 5/9. My apologies. I flipped that. Is equal to times 9/5. That's it. There's no add 32 to it. So all you do is take whatever the temperature difference is in, well, Celsius degrees, technically, these are Fahrenheit degrees, and multiply it by 9/5. So if there's a change in 100 Celsius degrees, divide by 5 gives you 20. 20 times 9 is 180. The change in Fahrenheit is 180. If you think about it, that kind of makes sense, right? How many degrees between the boiling point and freezing point of water? In the Celsius, water freezes at 0 Fahrenheit, boils at 100, Celsius, boils at 100 degrees Celsius. So there's a 100 Celsius degree difference. In Fahrenheit, it freezes at 32, it boils at 212. Subtract those two numbers, is a 180 degree difference. So 100 Celsius degrees is 180 Fahrenheit degrees. But the thing to remember most importantly is convert, whenever you see a temperature like this by itself, not a delta T, just temperature, Kelvin. Right? That's the safe bet. Make sure that it's in Kelvin. Other questions? Scrolling down, talks about, you have the tables on page, in your book 474 that goes in detail, converting Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin, and so on. So bookmark that or write that down on a note sheet if you're not sure about that. Talks about ranges in temperature. Thermal expansion's next. So this equation deals with next thermal expansion. You will either be asked in a problem, if I give you a problem like this, you will either be asked to find alpha, or I will give you alpha, right? You do not need to write down in your note sheets all of the alpha values for, oh, what's the linear expansion of brass? Oh, what's the linear expansion of lead, right? You don't need to know those. I will either give them to you in the problem, or you will have to solve for it. That'll be your unknown. The units for delta L and L naught just have to be the same. Obviously, it's best to convert to SI units, but remember to be careful if I ask you for something in centimeters, what is the change in length in centimeters, then that's what the answer has to be in. But alpha has units of 1 over Celsius degrees or 1 over Kelvin times Celsius degrees or Kelvin, so that those units cancel. So whatever unit you have L naught in, delta L will be in. If you measure L naught in meters, delta L will be in meters. If you measure L naught in miles, delta L will be in miles, and so on. Volume expansion, the equation is very much the same. The change in volume is the original volume times beta times the change in temperature, where beta is 3 times alpha. So this is just growing in 3 dimensions, right? The length is increasing, the width is increasing, the height is increasing. So the volume will just be 3 times that alpha constant. And that's called the coefficient of volume expansion. Water has a weird thing. The water's slightly different. Most materials follow this rule. Water actually becomes most dense at 4 degrees Celsius. And actually expands, ice expands as it freezes, which is why ice cubes are less dense and they float in a glass of water. But almost all the other materials follow this rule. And again, I'm just going through the book, the major equations, pointing them out, talking about what you need to know, and common errors. If you have a question or something, I say something that doesn't make sense, or you have a question, if you're following along in your book, you're like, oh, what about this? Let me know and we'll stop and talk about it.
Can you just explain what the step in the middle was about?
Yes, it's just the discussion about the difference between T and delta T. T has to be in Kelvin. Delta T doesn't have to be in Kelvin because 100 Celsius degree change is the same as 100 Kelvin. The step sizes are the same. So be cautious when you're doing a conversion. If I give you, say, delta T 10 Celsius degrees, and you're like, oh, I've got to convert temperature to Kelvin, you don't want to add 273.15 to that, right? Because the step sizes are the same. So you have to be cautious. If I give you 2 temperatures, it's best to convert those temperatures and then find delta T. Do not find delta T and then try to convert it. That's where most people make mistakes. So I give you 2 temperatures in Fahrenheit, and we did that for the linear expansion lab yesterday. If we give you 2 temperatures in Fahrenheit, convert them to Celsius first, or convert them to Kelvin first, and then take the difference. That make sense? Thank you. And then, when converting between Fahrenheit and Celsius is temperature, this is the equation you use, 9/5 the temperature in degrees Celsius plus 32. But if you're converting a delta T, this is delta T, there's no plus 32, it's just 9/5. So the next equation your book hits up on is the ideal gas law. Now, if you've had a chemistry class, this has been drilled into you, I'm sure. But physicists have a slightly different version. PV is equal to NK, sometimes K sub B, times temperature. Pressure times volume is equal to, capital N is the total number of particles. And K sub B is called Boltzmann's constant. I think two N's. I always forget how to spell it, and then I look it up. I'm like, oh, that's how I spell it. And then I get back to it. I'm like, wait, what was it again? And I will do that probably till I die. So, Boltzmann's constant. Boltzmann's constant's given. And one thing you definitely want to do, I've given you that constant sheet. Remember, it's on the D2L page, the two-sided constant. Be sure to print that off and have it with you on these exams. Because Boltzmann's constant, I will not give you right on a test. Because you have it on that sheet. And you have it in your, you can look it up in your textbook ideally, but hopefully you have it in that constant sheet. So if it's a constant in the sheet, like the mass of the electron, or the gas constant, Boltzmann's constant, those things, it's 1.38 times 10 to the minus something, 23?
23.
23, I was right?
Yep.
Yay! 23, and it's joules per Kelvin. So this is the physicist version of the ideal gas law. It deals with number of total particles. In chemistry, you're not counting particles, right? You have moles. You probably learned about moles in chemistry. So you have the chemist version, PV equals small n RT, where n is the number of moles, small n is number of moles, and capital R is the gas constant, which from memory, 8.31 joules per mole Kelvin, I think. Again, might not be exact. Check on the database. So, welcome. We just started a little bit early, but absolutely welcome to sit in if you have any questions as we go along. We're just starting with chapter 13. So, ideal gas law, right? PV equals N sub K, KBT, or PV equals nRT. T is in Kelvin. Pressures are in pascals, newtons per meter squared. Volume is in cubic meters for SI. Problem, very few people use cubic meters when measuring the volume of anything, with the exception of maybe the interior of a refrigerator. You go to Home Depot and see how many cubic feet or cubic meters the refrigerator's in. Right, in chemistry, it's mostly liters or cubic centimeters or something. So be sure you know how to do those conversions. Whenever you're converting a cube of something, you have to convert it effectively 3 times. Right, so if I convert 3.0 meters cubed, and I want to go into centimeters cubed, right, 100 centimeters for 1 meter, but I have to do that 3 times to get rid of all 3 meters. So I'm effectively multiplying this number by 1,000,000, not 100. So be comfortable with unit conversion, be comfortable with chain link conversion. You're going to have to convert some units. I'm not going to give them everything to you in SI. Pressure, typically there was that one problem. The difference between pressure, there's gauge pressure and regular pressure. We'll talk about that in a bit. But this is usually measured in atmospheres, typically, but you have to learn how to convert that into pascals. It's 1.013 times 10 to the 5th pascals per atmosphere, approximately. So in these types of problems with the ideal gas law, you're often asked to find how does the temperature change when the volume changes by this amount? Or how does the pressure change when the volume changes by that amount? So a good way of doing that is just setting up ratios. P1 V1 is equal to N1 R T1 over P2 V2 is equal to N2 R T2. R's automatically cancel. And then it's just a matter of What's constant in that problem? Is it an enclosed gas? The gas can't escape? Then the number of moles doesn't change, and you can cancel that. Oh, what if the volume stays the same? It says it's a solid container. Oh, the volume doesn't change. That's constant. Now you have a relationship between pressure and temperature. Or maybe it wasn't, the pressure stayed the same, but the volume changes. Then you would cancel the P's, and you would measure, you keep the V's, a V1 equals T1, V1 over V2 is equal to T1 over T2, and so on. And then you can solve for the unknown. If you're given moles, if you're given number of particles, then of course you can convert that. And it's fairly easy, right? Number of particles is just equal to the number of moles times Avogadro's number. And Avogadro's number is given in your, 6.02, right? Times 6.02 times 10 to the 23 particles per mole. So ridiculously high number of particles per mole. So you can easily go from number of particles to moles and back and forth. Questions on that?
So small n is moles.
Small n is moles, big N is the total number of particles. So if n was 1 mole, that means big N is 6.02 times 10 to the 23 particles. And the reason this is done is physicists often talk about first principles, talk about a trapped gas, and they can, since it's theory, they can put as many particles as they want in there. Whereas chemists actually deal with experiments where a mole is a useful unit in a chem lab, right? You can have a mole of water or a mole of gas. That's something you can wrap your mind around as a physical quantity. And it talks about the ideal gas law restated using moles. There's a derivation. It basically goes down to talk about the average kinetic energy. So in a gas, it talks about what temperature is. Temperature is a measure of the average kinetic energy of the particles in the substance. How much do they wiggle? That's what temperature is. So when something is cold, the particles don't wiggle as much as if something is warm. In a gas, the wiggling basically comes from the kinetic energy. So the average kinetic energy of the particle is 3/2 Boltzmann's constant times the absolute temperature. So if the absolute at absolute zero, classically, there is no kinetic energy in a particle. Particles stop moving. This doesn't really happen in quantum mechanics, but we're not worried about quantum mechanics. As temperature increases, the average kinetic energy increases. Again, this deals with T alone, so it has to be in Kelvin. So, for example, if I told you the temperature of a gas, you could tell me what the average kinetic energy is, and then if I say, but it's hydrogen, or let's say helium, it's a helium molecule, what is the velocity? Well, the average kinetic energy is 1/2 mv squared. So if you know the mass of the particle, and if I give you the mass of helium, you can actually tell me what the speed of the average speed of a helium molecule is. For oxygen, bigger mass, same kinetic energy. The average kinetic energy, you can see here, does not depend on the mass of the molecule. It just depends on the temperature of the gas. So the bigger the mass of the molecule, the smaller the speed has to be. So in this room, if there are any helium atoms in this room, and there might be, they're flying very quickly through the air and bumping into things very rapidly, whereas the heavier oxygen molecules aren't traveling quite as quickly. And if you have something really heavy like radon, it would be traveling much more slowly. And they're all bouncing together. Questions on this? Talks about phase changes, triple point of water. We didn't work any problems on that, I don't think. We did work on problems with heat transfer. Vapor density. All right, that's 13, moving on to 14. Heat and heat transfer methods. The concept of heat. So heat is like work. There are two ways you can change the energy of a substance. You can do work on it, or you can heat it up. So heat just basically transfers. Imagine sitting a hot glass of coffee on a counter in your kitchen. Heat transfers out of that hot cup of coffee into its surroundings, heating up the air around it, heating up the table underneath it, and eventually the temperature will drop, right, until that hot cup of coffee cools and ends up being room temperature. Put a cold beverage, iced tea on the counter, heat transfers into the iced tea, warming it up until it's room temperature, right? Heat transfers from hotter objects into cooler objects. So temperatures can change, but when you add heat, and heat is often given by the totally intuitive letter Q, because of course that's in heat, the word heat all the time. Q is a measure of heat. The amount of heat added can change the temperature of an object. How much? Well, it depends on the mass. Obviously, more mass you have, it takes more heat to warm it up. It also depends on this value C called the specific heat. That depends on the material. And in this case, it depends upon the phase as well. We're going to be dealing with solids here, solids and liquids. So the specific heat is just how easy is it to heat up or cool down a material. Water actually has a pretty high specific heat. You have to add quite a bit of heat to water to change its temperature. And because water has such a high specific heat, it takes a while for water to cool. It's one of the things, especially if you live near the lake. I grew up in Sheboygan, Wisconsin. If you live in the Milwaukee area and so on, especially near the lake, you always hear the weather people saying, oh, it's going to be 90 in Fond du Lac, but cooler near the lake. Oh, it's going to be 75 in Fond du Lac, but cooler near the lake in the summer. And in the winter, it's warmer near the lake. That's because Lake Michigan, it takes so long for the sun to warm up Lake Michigan all summer long. Right now, it's actually in a month or so, Lake Michigan will be at its almost warmest point. And then once the cold weather hits, it takes a long time for Lake Michigan to lose that heat. So it heats up its surroundings in the winter, and it cools off its surroundings in the summer. Because water takes a long time to generate, high specific heat, so it takes a lot of heat to change the temperature. Specific heat, in problems, I will either ask you to solve for the specific heat, or I will give you the specific heat. Again, that's not one of those things you need to write down, the table of the specific heats of all these substances. There's a delta T. So usually specific heats, SI, they're usually in Celsius degrees or Kelvin. So make sure your temperature change is set up to use the same units as the specific heat has, right? Mass is in kilograms. So make sure mass is in kilograms for this equation. And I say if I put a certain amount of heat in 10 kilograms of water, what is the change in temperature? You can tell me that. Or the temperature started off this, what is the final temperature? You can tell me that. Questions?
So one, I can't remember what chapter it was, but when we would calculate flow, was that also Q, the variable?
I think your book did use that as well, yeah. So it's context dependent. So heat, transfer of heat, you do use Q, so you have to keep that. Again, when you write your equations out, if you put this equation in your worksheet, if you're not sure what Q it is, write it down underneath. Q is heat. Should have these units. You can give yourself notes, so when you're going through, it's like, oh, I know T and M. I have the specific heat. Oh, I can figure out the heat. Having not just this equation on its own, but having a little thing underneath saying Q is heat, M must be kilograms. Specific heat, Aaron said he'd give this to us. Delta T, make sure that's in, you can give yourself little notes on those equations, which can be helpful. Because during an exam, you don't want to be like, oh, what did Aaron say again about that? Right? You want it listed right there. Other questions? So, this works if there are no phase changes. So when you heat up water or cool down water to a point, right, you can add heat to increase the temperature of water, you can remove heat to lower the temperature of water, but eventually you hit a point at standard temperature and pressure that occurs at 32 degrees Fahrenheit, 0 degrees Celsius for freezing, 100 Celsius, 212 degrees Fahrenheit for boiling, where adding heat no longer changes the temperature, but literally changes the phase of the material. So heat added is equal to latent heat of vaporization times the mass, or the latent heat of fusion times the mass. So this is for boiling or condensing. This is for freezing, melting. Notice there's no delta T there, because during these phase changes, temperature doesn't change. Think of a pot of boiling water, right? You heat up water on your stove, it gets to the point of boiling, it gets to 212 degrees. Your flame is still on underneath it, right? You're still adding heat. What happens to that water? It begins to boil. Boiling, people think of it as a heating process. Boiling is actually a cooling process. The water boils to keep the temperature at 100 degrees Celsius or 200 degrees Fahrenheit. So adding more heat, what happens is those water molecules break out of the liquid, turn into a gas, and fly away and take heat with it, take energy with it, keeping the water at a low temperature. So during phase changes, if you know how much heat you add, and you know what the latent heat of vaporization is for, like, for example, water turning into steam, or the latent heat of fusion, water turning into ice, or ice turning into water, will tell you how much mass you convert. So the diagrams that are often shown, for water especially, so time and temperature. So over time, let's say 100 degrees Celsius, 0 degrees Celsius. Let's take something out of your deep cooler, which is at minus 40 degrees Celsius. That's actually 40 degrees Fahrenheit, minus 40 degrees Fahrenheit as well, right? If you add heat, you have ice, but that ice warms up. People think often ice is 0 degrees Celsius. Well, no, that's the warmest ice can get. Ice can be actually much, much, much colder. Right, if your freezer is set to minus 40 degrees Celsius, the ice in your freezer is minus 40 degrees Celsius. So as you add heat, ice warms up, but it's still ice, assuming you're adding the heat slowly and uniformly over the block. Then you hit a phase change where the temperature doesn't increase. You're still adding heat, but the ice becomes water. After all the ice has become water, then the water heats up until it hits 100 degrees Celsius. Then you have another phase change where water becomes steam. And then, depending on the type of gas, if it's constant volume or constant pressure, the gas will get hotter and hotter. So steam isn't necessarily at 100 degrees Celsius. You can actually make steam much hotter than that. Now these boiling points and freezing points can change depending on where you are on the earth or what the pressure is, right? If anyone's ever used a pressure cooker, the whole point of a pressure cooker is you increase the pressure of the cooker and you increase the boiling temperature of water where the phase change occurs at a much higher temperature. So you can actually cook your noodles at, or cook whatever you're making in the pressure cooker at 110 degrees Celsius or 120 degrees Celsius. If you live in Denver, Colorado, the mile-high city, atmospheric pressure is lower, so water actually boils not at 100 degrees Celsius, but a few degrees below that. So that's one of the reasons cooking instructions are, oh, cook your noodles for 8 minutes, 10 minutes if you live in Colorado, or 10 minutes if you live above this elevation. Because since you're cooking them at a lower temperature, they have to cook longer. Questions on that? Just want to make sure this is still recording. Hello, wake up. There we go. This is not going to be a small file. Let's see what YouTube does. So that thing I just drew is in your textbook on page 528. Talks about problem-solving strategies for heat transfer. On page 531, I recommend going through those 7 steps, just so you have a comfortable doing those types of problems. There are 3 heat transfer methods: conduction, convection, radiation. Your book only really gives you equations for 2 of them. Make sure you use the same equation your book gives. So heat divided by time is equal to K times A, and what is the thickness, T2 over T1, over the distance. So, for example, looking at a house, looking at a wall of your house, it has some thickness, D, thickness of the wall. There's a cross-sectional area, A, right, how much surface of your wall. So these brick walls, right, there's some surface area A, there's some thickness D to those walls. K is a constant that depends on the material. Again, that's something I would give you. And this basically talks about how quickly heat transfers as a function of time. So this is basically in watts. It's a power transfer. How much, the rate of heat loss. Of course, you want a house that's well insulated. You want a house that the heat loss is very small. You lose a small amount of heat over a unit of time. To do that, you either need a small surface area. If you ever wonder, like windows in northern Wisconsin tend to be small, especially in old houses, because windows were an easy way to lose heat. So to minimize heat loss, windows are small. The temperature difference has to be small, right? If there's no temperature difference, there's no heat transfer at all. If T1 and T2 are the same, that becomes 0. So the bigger the temperature difference between inside and outside, the bigger the heat loss transfer. It depends on the material. Right? That's why we make materials that have well-insulating properties. Glass is not a great material. Concrete's okay. Wood's a bit better. And inversely dependent upon the thickness. So the bigger the thickness, D, the smaller the heat transfer. So the thicker your walls, the better insulating they are. So again, it depends on the cross-sectional area, the thickness, temperature difference, and this material-dependent K. Some materials are great conductors of heat. Well, if you think about it, this is conduction. This is heat transfer through contact. Some materials you want to be good conductors of heat, like your frying pan, right? You don't want a frying pan that is poor at heating up, but the handle of your frying pan, you'd prefer it to be poor at transmitting heat, right? You don't want to reach down, grab a frying pan handle, and burn yourself. And there are different ways and different materials that they can use to minimize heat transfer. So copper also, I mean, things that are good electrical conductors are typically good heat conductors. Glass is a terrible heat conductor compared to like copper. Questions on this? Yes.
Well, I actually had a question back to like the phase changing
Yep.
heat. So let's say I had a problem where I had ice and it's heated up to like 50 degrees Celsius, but I have to calculate Q with the latent heat of formation times mass and then add it to what I get for Q using M times C.
Yes. So if you had some block of ice, let's say it started at 0 degrees Celsius, Oh, let's say minus 10. Let's make it a little more complicated. Let's say a block of ice started at minus 10 degrees Celsius. You would first have to calculate how much heat was necessary to bring that block of ice up to 0 degrees Celsius using the specific heat of ice. So Q is equal to C times the mass of the ice times delta T, and delta T would be 10 Celsius degrees. Then you have to calculate how much is necessary to melt that quantity of ice to make water. So that's the latent heat of fusion for ice times the mass of the block of ice. So that heat is added to your first one. And then now you have water, you have to calculate how much heat was needed to take that mass of water up to 50 degrees Celsius. And then add that heat. So you have 3 different steps in that problem. Other questions? Convection, I don't think there are really any equations that we dealt with convection. Convection just talks about wind chill, basically that convection is the large-scale transporting of heat due to currents of air or water, some fluid. You've all experienced this with wind chill, right? If you stand outside on a still day in the winter, it feels much warmer than if it's a brisk wind. Because while the air temperature is exactly the same, a wind removes heat from your body more quickly than air does. It's the same reason that we can sit in a room at 70 degrees Fahrenheit and feel comfortable, but you get into a pool that's 70 degrees Fahrenheit, you feel cold. Because the water removes the heat from your body faster. When we think of things as hot or cold, we actually, as humans, don't measure their absolute temperature. We're measuring how quickly do they add or remove heat from us, right? If you've ever seen those people who walk on hot rocks, right? You have the bonfire and they have these lava rocks and they're walking over. It's like they're walking on basically fire. How can they do that? Those lava rocks, that pumice, are incredibly poor transfers of heat. So heat doesn't go quickly from those rocks to the bottom of your feet. You still have to cross pretty quickly. You can't just stand there. But if you had, say, blocks of metal in there instead of rocks, you'd instantly burn your feet as you tried to walk over because that transfers energy a lot faster. I think the example I used in the lecture videos talked about silk sheets versus flannel sheets, right? Silk sheets are actually really good at transferring heat. So on a warm day, or on a cold winter day, climb into the silk sheets, you feel cold because the sheets feel cold because they're pulling heat from your body more quickly. But the sheets are, of course, room temperature. They've been sitting in the room for a while. They aren't cold. They're just pulling heat from you more quickly. Flannel sheets, more insulating. So when you get into them, they don't feel as cold. They're the exact same temperature as the silk sheets because they're in the same room, but because it's not pulling heat as quickly, it feels warmer. That makes sense? And then finally, the last one, radiation. Radiation for heat transfer. We all radiate. Everything with a temperature above absolute 0 radiates energy. So again, you want to make sure I'm using the same equation as your book, same variables. Sigma E AT. Sigma is called the Stefan-Boltzmann constant, no relation. And again, that's given in your constant sheet. E is the efficiency of heat transfer. It's a number between 0 and 1. Has to be between 0 and 1. A is the total surface area of the object, and T is the temperature, again in Kelvin. So the only way you don't lose heat from radiation is if you have a temperature of absolute 0, and you don't. Things cool off through conduction. But you think of a hot cup of coffee, why doesn't it, if I put a hot cup of coffee, it'll cool off, it'll radiate some of that energy away. Convective currents take some of the energy away. Conduction with the surface takes some of the energy away. Why doesn't that hot cup of coffee keep on losing energy and eventually freeze solid? Because while it's radiating energy, so is everything else around it. So are the walls, so are the ceiling of this room. And so it's absorbing energy. Eventually it starts absorbing energy at the same rate it's radiating it out and reaches equilibrium. It comes to room temperature. But if you're trapped in space, we think of space being cold. Actually, it's not, because the temperature doesn't work quite the same way, because in space, there's very little conduction because there's no air up there to take heat away. You would basically slowly radiate away your heat. But that takes a long time. So this is radiation. This is conduction. This is radiation. So the efficiency is just how efficient is the surface of the material at emitting or absorbing. Things that are good emitters are good absorbers. Oh, yeah, question.
Yeah, I was just gonna ask, so it's T to the 4th, so is that another time where it's temperature in Kelvin?
Yeah, absolutely. It's not delta T. Temperature has to be in Kelvin for this to work. Otherwise, imagine if it were minus 10 degrees Celsius, threw a negative 10 in there. I guess you're putting it to the 4th power, so the negative will go away. But you could have a negative heat transfer. You can't do that. It has to be in Kelvin. Now, white t-shirts versus black t-shirts. If you've ever been outside in the summer, you know that wearing a white t-shirt is much cooler than wearing a black t-shirt. Black t-shirts absorb much more energy than white t-shirts do. But they also radiate their energy faster. So if you're overheated, if you're in the shade with a black t-shirt, you will actually cool off faster, or the t-shirt certainly will cool off faster than the white t-shirt will. So it's a matter of how efficient the material is, or the color of the material. So a efficiency of 1 is called a perfect black body. Efficiency of 0 basically is an object that isn't radiating, and I don't think that those exist in nature. So and then it's chapter 14. Questions on that at all? Yep.
So there's an equation given for radiation in the book that's Q net.
Oh yes, that, what'll happen is it almost looks identical to this, except Q net. So it's Q absorbed minus Q emitted. Right, so if you absorb more than you emit, your heat will go up. And Q absorbed would be sigma E A T to the 4th of the environment minus sigma E A T to the 4th of object, U, will be J. And then you can pull out, so delta Q net, or Q net, delta Q or Q net. It would be sigma EA, and then it's T probably environment to the 4th minus T object to the 4th, because you just algebraically pull out those things beforehand. So if an environment and the object are the same temperature, there is no net heat transfer. The object stays at the same temperature. If the environment is hotter than the object heats up. It gains heat and will increase heat. If the object is hotter than the environment, there's a net loss of heat. The object will cool off, just from radiative effects. YouTube won't flag, oh, you were drinking a Coke. Do you have the permission to drink Coke? Well, I'll take your video now. So you can prove you can drink Coke. I don't think they're that anal about it, but. Okay, so moves into talking about the first law of thermodynamics. Where the change in energy of a system, delta U, is equal to the heat added to the system minus the work done by the system. So this is total energy. Q is heat added to system. And this is work done by the system. And I stress by because it's negative, right? If a system does work, it's going to lose energy, right? Clean your room as a child. The child says, "Oh, I'm so exhausted. It's been half an hour cleaning up Legos," right? Energy goes down because they've done work. Some books, this is a plus sign because it's the work done on the system. So when you do work on a system, you add it to its energy. So it depends on the textbook publisher. Most of my textbooks, it's a plus sign. Yours is a minus sign. Again, it's just preference. So there are two ways to change the internal energy of a system: do work on it or add heat. And your book talks about this. Chapter 15 goes through how much heat or how much work it does, and so on. Talks about the first law of thermodynamics, and it goes through the PV diagram. So you're introduced to what's called the pressure volume diagram. And the simple setup is you have some container of gas that has a piston that can move up and down. So you can place some mass on this piston, and then that will change the pressure in that system. You're doing work on the gas if this moves up and down. You're compressing the gas or you're releasing the gas. So a PV diagram is a diagram of pressure versus volume. So you can have some point, we'll call it point number 1, where the pressure is high, but the volume is low. And then we have, let's say, point 2, where the pressure is lower. Here's P2, P1, this is V1, here's V2. And you have some process by which that occurs. You can occur at constant temperature or something along those lines. But to figure out the work done on the gas is the area under this diagram. So if it's a constant pressure situation, right, the pressure doesn't change, you have 1 and 2 here, let's move the volume over. So it just goes up and increases in volume. That means that positive work was done, and you just have to calculate the area under this. If you know what V1 and V2, let's call it V3 and V4. And you know what P3 and P4 is, 3 and P4, which is the same, because this pressure hasn't changed. You can then just, area, like length times width, get the area of the rectangle and figure out how much work was done. So work is equal to P times delta V. Technically, work is the integral P dV, but that's calculus, and we're not going to stare with calculus. So we're going to assume, if the pressure stays constant, the change in volume times that pressure gives you the work done on the gas. And there are examples of this on page 566 of your textbook. Constant pressure is often referred to as isobaric. Iso being constant, baric, think of it like a barometer. What does a barometer measure? It measures pressure. That's where the baric comes from. So an isobaric process is a constant pressure. Isothermal, anyone have a guess what isothermal means? Constant temperature. And then constant volume is usually just referred to as constant volume. Your book begins by talking about heat engines. Now, I'm not going to go through the details of a heat engine because I'll be basically just recreating the lecture on heat engines. And if you want me to see that lecture on heat engines, you can just watch that lecture. But we'll summarize the equations that come out of the heat engine. So heat engine is basically a process by which you can do work by taking heat from a hot source and dumping it into a cold source. That's how cars work, right? Your car engine uses gasoline to create a small explosion of hot gas to create a very, very high temperature gas. It then uses that hot gas, does some work with it, and then dumps the remainder of the hot gas into the cold reservoir, which is the atmosphere, right? So if you've ever been in the back of a car, you can feel the hot exhaust, the hot air coming out of the back of the car. That hot air has already expended a lot of its energy pushing, the pistons, pushing your car forward. So there's what's called an ideal heat engine. It's called a Carnot engine. It's French, so we don't pronounce the T. And the efficiency of a Carnot engine is 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. In Kelvin. This one trips up a lot of people who want to use Celsius. This only works if the temperatures are in Kelvin. That basically means that if your cold reservoir is at absolute zero, your engine efficiency can be up to 100%. If your hot reservoir is infinitely hot, your efficiency can be 100%. But in reality, that temperature of the hot reservoir is how hot does the gas get in your little compressed cylinder. It can get a few, probably hundreds, several hundred or thousands of degrees Kelvin, depending on the type of engine you have. Temperature of the cold reservoir is air temperature, 300 Kelvin-ish or so. So this just means that you cannot have an infinitely efficient heat engine. That, depending on the temperature, reservoir temperatures, this is the maximum efficiency you can do. So car engines have an absolute maximum efficiency that you cannot exceed. We haven't gotten to that efficiency yet. We're probably 10% of the way there, or 20% of the way there. But once we hit that maximum efficiency, we literally can't make a better car. We won't be able to make a better car. The laws of physics won't allow us to do that. Questions on this? So once you figure out the efficiency of an engine, let's say your engine's 30% efficient. That just means that if I put 100 joules of heat into the engine, I'll get 30 joules of work out of that engine. The rest of the heat is just lost into the cold reservoir. So that's the most efficient type of engine called a Carnot engine. And then there's the Carnot refrigerator. There's a heat pump, ideal heat pump, or Carnot refrigerator. There's put a D in there, refrigerator. Probably is a D. I probably totally misspelled that. But I ain't an English major. What was the Simpsons quote? Me fail English, that's impossible. Carnot refrigerator deals with what's called the coefficient of performance. And again, I want to make sure that I use the right variables. Doesn't have it in terms of temperature, that's interesting. Where does your book have coefficient of performance? Pumps. Sorry, one second. pretty sure the coefficient of performance was the temperature of the cold reservoir over the temperature hot minus temperature cold. I have to double check that. So it depends upon, yeah, heat pump minus 1. So basically, from the efficiency of the heat pump, so this breaks down the temperature cold over temperature hot. Minus 1? No, that's not how it works. I can do fractions. So this, while the efficiency can be between 0 and 1, you can't have an efficiency below 0, you can't have an efficiency above 1 for a heat engine. The coefficient of performance can be above 1. And in fact, that's something that's often advertised on like air conditioning units and refrigerators. So basically, a coefficient of performance says that if you put in 100, let's say you have a coefficient of performance of 10. That means if you put in 100 joules of work into the system, you can remove 1,000 joules of energy. So basically means that it's a factor of 10 efficient, where for every joule of energy you put in, you can pull 10 joules of heat out. Well, where does that go then? If you put 100 joules in, you pull 1,000 joules out, that's 1,100 joules of energy you're sitting on, that's dumped into the hot reservoir. So for a refrigerator, your refrigerator has to be plugged in because there's a compressor that does work on a gas. For every joule of energy your refrigerator puts in, it might pull 10 joules of energy out of the interior of the fridge, cooling it off, 10 joules of heat energy, and then spit out the combined 1 plus 10 or 11 joules into the air to the back of the fridge. Question? No? Okay. Questions? So that's coefficient of performance. The efficiency has to do with heat engines. Coefficient of performance has to do with heat pumps. Heat pump is basically trying to go against the laws of thermodynamics. Heat engine goes with the law of thermodynamics, which is the second law of thermodynamics, which basically states that heat moves from hot objects to cold objects intuitively, right? Intrinsically. If you have a hot cup of coffee and you put it on the counter, you come back an hour later, you're not going to expect it to be hotter, right? You put a cold drink on the counter, you come back a few hours later, it is not a frozen block of ice now. Unless you left the window open and it's Wisconsin winter, right? At room temperature, heat transfers from hot objects to cool objects. So, to be pedantic, of course, you talk about leaving the door open in the winter. It's like, oh no, you're going to let the cold air in. It's like, well, no, heat transfer. You're going to let the hot air out. Heat transfers in that direction, from hot to cold. So to get it to transfer from cold to hot, like your refrigerator, to get that refrigerator to be cold, you have to do work. You have to put work into the system in order to remove heat from a hotter object and dump it from a cold object and dump it into a hot object, because you're going against the laws of thermodynamics. Does that make sense? If it doesn't, now's the time to ask.
I'm a little confused with the equation given for it.
Okay.
I'm just looking at the ones our book gives.
Yeah, your book doesn't do this version.
Okay.
It talks about Q cold over the work done. But for an ideal Carnot refrigerator, basically what it means is if the temperature of the hot and cold reservoirs, for example, you have a fridge that you just bought. The interior of the fridge is the same temperature as the air in your kitchen. As soon as you plug in that fridge, it's really easy to pull heat out of that interior because it's the same temperature as the outer. So the coefficient of performance will be quite high. However, as this temperature difference gets bigger and bigger and bigger, it's much harder to pull heat out. If you ever had like a small window air conditioner unit, it's 100 degrees outside, that little air conditioner unit might not be strong enough to keep up that temperature difference anymore. It might not be good enough to keep that room cold. And then the coefficient of performance depends upon the temperature of that reservoir as well. This question.
Another equation they gave is the COP HP is equal to QH over W.
Yeah, QC is the heat pulled from the cold reservoir over the work done.
Okay, so that's just another way of
Yeah, in other words, this is in terms of temperature.
Got it.
Yeah. So if you know, well, like I wrote it out here, COP. It's the temperature pulled out of the cold reservoir, which in this example is 1,000 joules. Over the work done to do it was 100 joules. 1,000 divided by 100 is 10.
Got it.
There's a second law of thermodynamics that talks about the concept of entropy. Entropy, roughly speaking, is the amount of disorder in a system. The second law of thermodynamics states that in a closed system, the entropy either remains constant or it increases with time. So the change in entropy, your book gives, again, we're not doing calculus here, is Q, or the heat, over some average temperature. So if you add heat to a system, that will change the temperature of that system. Using an average temperature, you can calculate how much the entropy changes in that system. So let's say I add 10 joules of heat or 100 joules of heat and increases the temperature from 250 Kelvin to 260 Kelvin. Well, then I plug in how much heat I used, 100 joules, and I plug in the average temperature. If it's 250 Kelvin to 260 Kelvin, I would have to do 255 Kelvin. Again, temperature, so it has to be in Kelvin. It's not delta T. So the common way to describe entropy is a deck of playing cards. I think all of you in your life have shuffled a deck of playing cards, hopefully. If you haven't, then I know what you're doing with your life. Card games are great. So if you take a brand new deck out, right, they're in order. All the suits are together, increasing order. But you start to shuffle, then the cards become disordered. It is almost impossible to shuffle. In fact, you can actually calculate the probability, it's ridiculously small, of taking a randomized deck, shuffling it, and suddenly finding all the cards are in order. In fact, there are so many ways to shuffle a deck of cards. The number of possible combinations in a deck of cards is 52 factorial. So it's 52 times 51 times 50 times 49 times 48 all the way down to times 1. It's such a big number that when you shuffle a deck of cards well, the chances are that order that you just created has never existed before and will never exist again in the universe. So, pretty unlikely. So the fact that you try to shuffle them and get them in order again is ridiculously small. So it's easy to make things disordered. It's hard to make things ordered, right? You've never, knocked a vase off the wall, it shattered, and then just waited a while and suddenly the vase jumped up, put itself back together, and landed back on the shelf, right? It's not going to happen. Your room does not spontaneously clean itself. You have to put work and energy into it to reduce entropy. Now, these are for closed systems. So one of the big arguments I know creationists use, talking about, well, how can the Earth become more evolved with time? How can creatures become more evolved with time and more complex if Earth is a closed system? And the answer is it's not. The sun is dumping huge amounts of energy on us all the time. But the Sun-Earth system is closed, and that entropy is increasing. The sun is dumping huge amounts of heat out every second. The equivalent of a trillion 100-watt bulbs every second is the amount of energy the sun is dumping out. So that's entropy. Carnot engines. And there's a statistical argument of entropy. I don't think we really went over that very much, talking about different states. We talked about if there are no equations for that we have to worry about. And And that ends chapter 15, and we get into 16, oscillation, motion, and waves. Talking about springs, Hooke's law. So we move back to springs, which we've talked about already. And this deals with the stuff in the lab we just did today, right? So the force on a spring is equal to minus k times x, where x is the displacement from equilibrium position in the horizontal case, and k is spring constant. Again, small k we just use for Boltzmann's constant, right? So make sure you understand with the equations what these variables are. Right next to it on a cheat sheet, oh, this is Hooke's law, H-O-O-K-E-S, I believe. Hooke's law, where talking about the relationship. The negative sign just means that it's in the opposite direction, right? When we did the experiment today, when you pulled the spring down to start the oscillations, you displaced it in the downward direction, but the force then on the mass was upward, right? The spring wanted to pull it back. If you lifted it up, you're pushing it up, the force, gravity took over and wanted to pull it down. So that negative sign just means that the force is in the opposite direction of the displacement. That's the Hooke's law dealing with spring forces. For energy, how much energy we store in a spring we talked about yesterday, 1/2 spring constant times that displacement squared. So when you displace a spring, you store energy in that system. How much energy depends on how stiff is the spring. The stiffer the spring, the bigger the K constant, and how much have you displaced it from the equilibrium position. The spring is just resting in its equilibrium position. There's no energy in that system, no matter what the spring constant is. Because x is 0, so the spring energy has to be 0. Questions? So moves on to talking about period and frequency as concepts. They're inverses of one another. T, capital T, represents the period. Has units of seconds. SI units. Frequency has units of inverse seconds or hertz. Period is 1 over the frequency. Frequency is 1 over the period, and so on. So we talked about simple harmonic motion of an oscillator. You take a spring like the one we just did today, right? That spring was moving up and down. What is its period? Its period is 2 pi times the square root of the mass of the object over that spring constant K. Bigger the mass, the bigger the period. That was one of the results of today's lab. As you increase the mass, the period increases. K is that spring constant. These are both under the radical. Then, not surprisingly, since frequency is 1 over period, the frequency then becomes 1 over 2 pi square root of K over M. It's just the inverse of that problem. So the stiffer the spring, the slower it is, right? Big K means the frequency is low. You don't get a lot of oscillations per second, or the period is high, because K is in the denominator. And so the stiffer the spring, the smaller the period. Sorry, the higher the period, I apologize. Higher the period. The bigger the mass, the higher the period. These are linearly related. So big mass means big period. Big mass means low frequency. You should have noticed that when you put a lot of mass on today's experiment, it went slower. You had created that plot. Again, everything SI, right? Mass 8 kilograms. K, spring constant is in newtons per meter. Well, you have, let's just make sure the units work out. Mass over spring constant, so it's kilograms over newtons per meter. So it's kilograms, a newton is a kilogram meter per second squared over meters. Meters cancel, kilograms cancel, you have 1 over seconds, which goes to second squared, which becomes second squared. Take the square root of this, you get seconds, which is the unit per period. So it all works out. That's why it's important to make sure everything is an SI. If everything is SI, these equations just work out. You'll get the SI value for the frequency one, you'll get hertz out. For the period one, you'll get seconds out. If you don't use the SI values here, you won't get the right answers.
Aaron, you said that as the mass decreases, so does the frequency. Is that what you said?
Sorry, I went the other. I should have gone the other route. As the mass decreases here, the denominator gets smaller. The frequency should increase. So a light mass will go more quickly, whereas a heavy mass will be more slow. So I did flip that around in my head. Sorry. So then there's a derivation for what's called the simple pendulum. Because there is a thing called the physical pendulum, which your book doesn't really talk about. So the period is 2 pi, length of the pendulum over the acceleration due to gravity. And whenever you see g in an equation, they mean positive 9.8. The negative sign or the positive sign comes as part of the equation as to the direction of gravity. But g, whenever you see g, you plug a positive 9.8. If there's a negative sign in front of the g, then it will be minus 9.8. But there's no negative sign in front of this g. So this is the period of a pendulum that's swinging. Right, some mass. So I know what the mass is here. I set it some length. I know what g is on Earth, 9.8. So I can calculate, if I knew the length of that rope, I can calculate the period of that pendulum. What if I put a different mass on there? What's going to happen to the period of the pendulum? Is there mass anywhere in here? Nope, it's irrelevant. For a simple pendulum, mass does not matter. So you could actually measure the height of a building if you wanted to. Go to the top of the long enough rope, like a bowling ball hanging off the end. Hold one end of it, have someone down at the bottom, start move the bowling ball a little bit so it starts to get pendulum motion. Calculate the period of the pendulum. You could actually, what the period of that pendulum is, you could calculate the length of the rope. So you could actually measure how big something is or how tall a room is by the period of the pendulum. Make sure we're uniform circular motion, simple harmonic motion. Okay. Questions on any of this? Now I'm doing this fairly quickly, but we've already been here for more than an hour, so I don't want to keep you forever. You do have other things to do, I'm sure. But officially, we'd be doing our third lab now, so I don't feel guilty keeping you a little bit. But if you decide it's like this is boring, I am falling asleep and I have a long drive, if you have to head out at any time, I will not take offense. You can head out, but I'll stick around for a while longer yet and keep on doing this. So I just didn't want you to have to go. Oh, I don't want to be rude. No, be rude. It's not rude. Just go if you need to go. But we'll continue on. So we have simple harmonic motion, which is talking about an oscillator. So for example, that spring that was moving up and down, or imagine it horizontally moving back and forth. So mass on a spring oscillating back and forth from its equilibrium position. And we want to know, well, what is if this equilibrium position we set to be 0, this is a function of time, right? Depending on what time you take a picture, maybe the mass will be in the middle, maybe it'll be on one side, maybe it'll be on the other. The position as a function of time is equal to the amplitude times the cosine of, so again, sine, not cosine, 2 pi times the time over the period. Your book uses cosine for some reason. I'm used to using sine. It's not that different. Basically what it states though is at time of 0, cosine of 0 is 1, so the position will be at its maximum position. So the block would be over here at x equals x of m. Its maximum displacement at time 0. If that's the case, then I could, at any time later, if I knew what the period of oscillation was, which I can get from that equation over there on the right, I can tell you what the current position is of the mass at any time t. We're talking about damped harmonic motion. I'm going to skip over that to forced oscillations and resonance. We really know equations based on that. And then we talk about wave motion. So superposition and interference. Waves interact with one another. You've seen this if you've ever been to the ocean or a big lake or a wave pool or whatever. Drop a couple of drops of water in a still pond or a sink. You can see how the waves interact. So if you have 2 waves coming together, if they're in phase, you can get what's called constructive interference. Where you end up getting, when you add these waves together, you get a much bigger wave, higher amplitude. That constructive interference is what happened during the resonance in today's experiment. Why did the tuning fork suddenly start to sound a lot louder? Because you had the tube set up at some fraction of a wavelength, so constructive interference could occur and amplify the sound that was going into that tube. If they are out of phase by half a wavelength, so where the peaks occur on one, the troughs occur on the other, right? When you add these together, if the amplitudes are the same, you get completely destructive or total destructive interference. Some of you might have experienced this if you have a pair or if you've tested a pair of noise-canceling headphones. That's how these work. Noise-canceling headphones have a little microphone outside of the headphone that picks up the ambient sound. It then creates, inside the speaker, a sound that has a phase shift of 180 degrees or 1/2 of a wavelength, and plays that into your ear at approximately the same volume. So when you hear it, you get total destructive interference. It's not perfect. And it works best with sounds that aren't changing rapidly. Like, for example, if you're on an airplane, the drone of an airplane engine, these headphones work really well at helping cancel that noise. And I know at Best Buy, you probably have a local Best Buy where you live, have some of these on display. It's fun sort of to pick them up, put them on your ears. They're like, oh, these sound like normal headphones. But when you start to play something or turn them on, you can hear suddenly the room you're in just suddenly go quiet because the noise cancellation kicks in and then the music starts playing. So you can really experience that total destructive interference. Questions on this? No real equations to deal with these, just concepts. And then finally, beat frequencies. One thing about constructive and destructive interference, we're assuming these are the same phase and the same frequency. What if they're not the same frequency? What if you have two sounds that have slightly different frequencies? What you'll get is a beat frequency that's just the difference between those two frequencies. And if you've ever played guitar or a stringed instrument, you can use this to actually tune a guitar or tune a stringed instrument. So you play a note on one string, you push on the fret of one string to mimic the note on another string, and you listen when the pitch is higher or lower, so you tighten or loosen the string to change the pitch. But once it gets close, you can actually start to hear the beats between the frequency. Basically what will happen is you won't get completely constructive interference and it'll sound loud, or completely destructive interference where it sounds quiet. You'll get a mix of the two that oscillates, so the note will like wow, 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 and the closer you get in tuning, that will slow down, wow, and eventually if you don't hear it anymore, you know those two notes are exactly the same frequency. Sorry, my special effects are lacking, but questions on that? And if you want an example of that, I actually have some tuning forks in the back that have slightly different frequencies, and I can show you that before you leave. Intensities in waves. Assuming the wave is moving out radially, the intensity is equal to the power over the cross-sectional area. Power over area. This is intensity. Does anyone remember units for power? Watts. What about area? SI units. Meter squared. So intensity doesn't have its own unit. It's in watts per meter squared. This is why, if you've ever been to a rock concert, you might not want to stand right in front of the speakers at the front of the stage. Right? The speakers are giving out the same power all the time, but that power is concentrated near the speaker. So the intensity is much, much, much higher because all that power is in a small area. As that area increases, as the sound moves out over a broader area, the intensity drops. Light is the same way. The sun puts out a given amount of power every second, like I said, the equivalent of a trillion 100 watt light bulbs. The intensity of sunlight depends on the area that is spread out. Assuming the sun spreads it out radially, it's the surface area of a sphere the same distance as Earth's radius is, so 4 pi r squared, where the r is the radius of the Earth. The distance between the Earth and the sun. So that's the intensity. Double the distance from the sun, you drop because it's the distance squared there, the area, you drop the intensity by a factor of 4. That's why, in astronomy terms, we can't send spacecraft out into space that are solar powered much past the orbit of Mars. Jupiter's 5 times further away from the sun, the intensity of sunlight is 25 times weaker. So solar power just does not work out there. Where it's incredibly efficient, if you go into the inner solar system. I think NASA's going to launch a probe later this year that's going to get within 6 million kilometers of the sun. To give you a sense, right now we're 150 million kilometers away, so it's going to get much, much, much closer to the sun than we've ever been. It should be kind of interesting. And then that's the end of chapter 16. Questions on any of that?
We need to know anything with sound intensity about decibels.
I'm not sure if there's a decibel equation. We'll get to that in just a bit because you have sound level and sound intensity in chapter 17.
Next chapter.
Yeah, it's the next chapter. There might be a simple intensity equation in decibels. And decibels, honestly, it's kind of a weird unit. It's literally decibels. The SI unit is actually a bell, and it's a tenth of a bell. But for some reason, that's because decibels are on the scale of human hearing from 0 to 100. 100s are fairly loud. Actually, 130 is probably the loudest sound you ever want to really hear. So that's why they went with decibels instead of bells. Because humans like scales that go from 0 to 100. We're happy with those. Right, so sound, talking about sound, it's an oscillation longitudinal wave. Speed of sound, which you of course measured. The velocity of sound is equal to frequency times the wavelength. So you can measure the velocity of sound in air if you know the wavelength and the frequency. So this is why if the instruments work, right? You set up a guitar string at a given wavelength when you push on a fret and pluck it. It vibrates at a given frequency depending on how tight the string is. That frequency changes to a higher note when you shorten the wavelength in air. It's why you sound ridiculous when you breathe in a helium balloon. I'm sure all of you probably done this as kids, right? You suck in helium and you sound like Mickey Mouse. Why? Because the wavelength, or sorry, the frequency of the oscillations of your vocal cords doesn't change, but the velocity of the air actually does, the velocity of sound, because helium travels much more quickly than normal air does, and that actually causes your pitch of your voice to increase or decrease. There's a gas that does the opposite. I forget what's called something. I want to say sodium hexafluoride, but I'm sure that's probably some evil toxic chemical, not the one I want. But if you breathe it in, it actually makes you sound much lower pitch. It's more dangerous though because it's a heavier gas and stays in your lungs, so it's harder to get out, and you can actually suffocate. Whereas helium naturally wants to get out. Sorry, a little aside there. So talking about sound intensity and sound levels. Again, intensity is pressure over area. So you have the decibel scale. There is an equation for decibel scale where the sound level in decibels is equal to 10 times the log base 10 of the intensity with respect to some reference intensity I naught, where I naught is 10 to the minus 12 watts per meter squared. Not 2, sorry. 10 to the minus 12 watts per meter squared. So if you know what the intensity is, or if I tell you what the intensity is, when you plug that in, you know what the reference intensity is. This you would have to have in your notes. You can tell me what the sound in decibels is. Or vice versa, if I give you the sound of something in decibels, you can tell me what its intensity is. Decibel ranges, the threshold of hearing, the reason this scale was chosen is because the threshold of human hearing is about that scale, which would give you a decibel rating of about 0. So 0 decibels is just basically the threshold of human hearing. There can be sounds less than 0 decibels. It's just that humans would not be able to hear them. And then with jet airplane or so, 130, 140 decibels. At 160 decibels, you're basically destroying your ears. And that type of damage is permanent. So classroom lecture, it actually gives it as 80 decibels, so that's what we're experiencing right now. So if I said my lectures were at 80 decibels, you'd be able to calculate the intensity of that sound on your ears using that equation. Other other questions? Finally, there's Doppler shift. When an object that's producing a sound is moving towards you or away from you, or you are moving towards or away from an object that's producing a sound, the pitch of that sound changes. So the frequency observed is equal to the frequency of the object, let's say emitted, times, and it depends, it breaks it down in two equations here. Usually I'm just used to having it in one equation. The velocity of sound in air, or the velocity of the sound in air, plus or minus the velocity of the source. This is if the source is moving. Frequency observed is equal to the frequency emitted, the velocity of sound, plus or minus the velocity of the observer over the velocity of sound. So this is source moving, and this is receiver moving. So receiver being the thing that's hearing the sound. Velocity of sound, 323 meters per second approximately in air. So it depends on the speed of the source with respect to the speed of sound. Plus or minus means that the source could be moving away from you or towards you. The observer, the receiver could be moving, observer could be moving away from you or towards you. If you're moving together, you're going together, either the source is coming to you or you're going to the source, frequency increases. Apart, frequency decreases. Again, I apologize for my bad special effects, but all of you have probably experienced standing on the side of a road or a highway and hear a car approaching. What do they sound like? It's like, right? The high pitches it's approaching you, lower pitches it's moving away. So, how do we get a higher pitch if the source is moving towards us? Well, we need a smaller denominator, so it's the minus sign. If the observer is moving towards, we need a small frequency increase. How do we get a frequency increase? We add the speed of the observer, right? Increasing the numerator increases the frequency. Here, decreasing the denominator increases the frequency. So you have to think about, how, do I add or subtract the velocity of the object? Well, are they coming together or are they going apart? You have to figure out adding or subtracting to get this result. Questions on that at all? And then your book talks about frequency, air columns, all that fun stuff we just talked about. Today's lab talks about hearing, which we really didn't cover much, pitch and so on. We really didn't have any problems on that. Ultrasound, we didn't really have any problems on that. Your book does have some interesting chapters on medical applications of these things, like ultrasound is definitely a sound wave. Ultrasound meaning it's a sound wave that's higher frequency than you can hear with the ear. Infrasound is a lower frequency. So elephants can communicate via infrasound at a lower frequency, or whales at a much lower frequency than humans can hear. Dogs can hear ultrasonic frequencies, right? Lower ultrasonic frequencies. Dog whistles, right? We can't really hear a dog whistle, but dogs can, because they have different range of hearing. So I always kind of wondered if you've ever gotten those There's some things you can buy for rodents where it puts out a really high frequency sound to drive rodents away. But they say safe for dogs, right? The idea is that if you have pets, you don't want to drive your pets crazy because of this high frequency sound. But how would you know? Because you're not going to tell you. So I hope they're safe for animals. I assume that the smaller animals would have a higher frequency range, but maybe not. And bats, of course, using their sonar. It's still recording, yay. All right. Questions on this? Well, that covers chapter 17. So you're ready for, so an hour and a half, you're ready for hopefully the chapter 3 exam. What I'll do now, again, you're free to go whenever you want. I don't want you to feel obligated to stay. But what I'd like to do is pause for a moment. Any questions that you might have about anything we've covered, if it's chapter 3 material. If no one has anything, or once we're done with those, we'll start in on chapter 1 stuff, go back to chapter 1 quickly and go through the major topics at a slightly faster rate. So we're done in a reasonable time. Yeah.
Can we just work through one example where you would give us decibels? So where I was struggling with for sound intensity was just working with logs.
Oh, okay, okay. So, I see what you mean. So, if I gave you decibels and you want to find the intensity, so inverse, okay, got it. So let's do the lecture. 80 decibel lecture. What's the intensity we experience? So 10 log 10 I over I naught. I want to know I give you the lecture is 80 decibels. So it's 10 decibels technically, log 10 I over this reference intensity, which is 10 to the minus 12 watts per meter squared. Okay, everyone happy with this? To solve this, what you want to do is get that log by itself on the right. So I'm going to divide both sides by the 10 decibels. So 80 decibels divided by 10 decibels. Decibels disappear, which is what we want. It's equal to log base 10 I over 10 to the minus 12 watts per meter squared. And of course, then this would be equal to 8, right? 8 log base 10 I over 10 to the minus 12 watts per meter squared. Everyone follow my math so far on that? The way to get rid of the log on the right-hand side is to do the power on both sides. So take that to the power of 10 on both sides. So on the right-hand side, you have 10 raised to the 8th power. On the left-hand side, on the right-hand side, you'd have 10 raised to the log of that, which the 10 and the log cancel, and you end up with just I over 10 to the minus 12 watts per meter squared. Because x to the log, 10 to the log base 10 of x is equal to x. Then you have 10 to the 8th, which is 100 million. 100 million, so 10 to the 8th, multiply both sides by 10 to the minus 12. So you have 10 to the 8th times 10 to the minus 12 watts per meter squared is equal to the intensity. Combining these, you get 10 to the minus 4 watts per meter squared is the intensity. Everyone follow along with that? Make sense? Okay.
Thank you.
Yep. No, it's after you've out of algebra, there aren't too many things that you have to deal with, certainly in the real world, that deal with logs, right? It's one of those math things. It's like, I used to be able to do that, but I remember learning about it. Other questions, examples?
Just kind of in general, for like everything for this midterm exam and like everything that we've covered, there've been a lot of like tables with like constants or numbers. I don't know if you've already said this, but is that something that you would give us, or do we need to like have those?
Almost certainly, if it's, unless like the default intensity there is always the same. So that's something you probably want to have in your notes. Or that's something that you could probably look up very quickly in the book if you didn't have it in your notes. But if it's like the linear coefficient expansion, or the mass of an oxygen molecule, or something like that, I'm not going to make you figure that out. That's something you're either going to be solving for, or that's something I'll give you in the equation. So like the thermal expansion coefficient for copper is blah. You have a 5-foot copper rod. How long does it get after you heat it to 20 by 20 Kelvin or whatever? Then you have to go through the math. But I'll give you those constants.
Okay.
Other questions? Okay. So, it's not going to be the most exciting video in the world. But all of you can say, I was there when he did it live. As I gain internet fame, goes viral. Actually, on YouTube, I think I have 3 followers. I think you have to have 4,000 a month visits to actually start getting money on YouTube. So I have a while to go. So going through quickly, chapter 1, physics introduction. I'm trying to think of where we start getting about that. Just talks about the basics of physics to get you somewhat interested. But then it talks about the SI units, right? The fundamental units of science that we're going to be dealing with, where mass is measured in kilograms, which throws people off because they're like, oh, base SI unit, that's gram, right? Because a kilo is a prefix. Nope, mass, kilograms. Length, meters. The time in seconds. And one last one we dealt with, quantity in moles. There are a couple of others. Luminous intensity in candelas, which no one ever uses. Now you're astronomers who study that stuff. And I'm trying to think of electric current in amperes, that sort of thing. But these are the base SI units. So all the other units derived from these base SI units. Forces in newtons, energy in joules, that sort of thing. Right? All of those work out if you stick to the base SI units. So when you're converting things for problem solving, don't convert to grams, convert to kilograms. Yeah, just going through quickly the pages to do prefixes. You know how to use the prefixes, what a kilometer is, what a megajoule is, be able to go, and that's why that worksheet I made for you is helpful to be able to go from what is a picometer, that sort of thing. Accuracy and precision, we covered that ad nauseum in lab. And approximation measurements, we didn't really do much with that. Then we went on to chapter 2, motion. Chapter 2 summarized in basically what are called the constant acceleration equations. There are 3 main ones, right? The velocity of an object is equal to the initial velocity of the object plus the acceleration of that object times time. Again, assuming the acceleration is constant. If the acceleration is not constant, we can't use these problems. But I'm not going to be asking you a question where acceleration is not constant because you don't have the tools. You need calculus to do that. You don't have those tools. And of course, if the acceleration is 0, then the velocity doesn't change. Right? The final velocity is equal to the initial velocity at all times if the acceleration is 0. Then we had x is equal to x naught plus v naught x times t plus 1/2 a sub x. I guess I could be a little explicit, talking about x direction here, t squared. Our second constant velocity equation dealing with displacement, initial velocity, and acceleration. And then finally we had v squared is equal to v naught squared plus 2 times the acceleration times the displacement. Our third constant acceleration equation. So this talks about motion in one dimension, either vertically or horizontally. If you know what the acceleration is in that direction, how long the object has been moving with that acceleration, what the initial velocity is of the particle, final velocity of the particle, initial position, and final position. So when you're solving these types of problems, you definitely want to have these equations in your notebook. We've used them quite a bit, your cheat sheet. But if you don't know what the displacement is, the first equation doesn't have displacement. So that might be the one you need to use. I mean, if you're not asked to solve for the displacement. If you're asked to solve for the displacement, you have to use equations 2 or 3, right? Because there is no displacement in 1. What if you don't have time? What equation would you use if you don't need and you don't have the time? The last one, because there's no time in that. So those types of equations for the final, write down what you know. An object starts from rest. Initial velocity is 0. It travels 5 meters. I'm going to assume its initial position is 0, its final position is 5 meters. Right? It gains to a velocity of 3 meters per second. That's the final velocity, 3 meters per second. What's the acceleration? I don't know time. Okay, I don't know time, but I know, I can use this. Right? I can use this to find the acceleration given the displacement and the velocities. So these equations are absolutely necessary to do well. I guarantee you there'll be a problem that deals with these equations in some fashion, either through free fall or for horizontal motion and projectile motion. The only difference in projectile motion is you have the y version of these equations where the acceleration is due to gravity. We'll talk about that in a bit. You have the x version of these equations where there is no x acceleration because the object's in free fall and there's no force in the horizontal direction. And you can use that to solve for the path of the particle. And we'll get to that in the next chapter. Vectors, how vectors work. Direction is important. To talk about acceleration. We also have, you might be, x is equal to x naught plus v naught times t. This is one of the first equations given in chapter 2. Note, it's very similar to the middle equation here. In fact, it is the middle equation if there's no acceleration. So I would not put this in your notes if you have this, because this is the better equation. This works in all cases. This only works, or works with constant acceleration, regardless of what the acceleration is. This one only works if the acceleration is 0. So I've seen people pull this one out when it's a free fall problem and get the wrong answer because it does not contain acceleration. I talked about reference frames moving. There's a problem similar to, I think one of the problems actually on the exam was a canoe. There's a river that moves like 5 miles an hour downstream. You're on a kayak paddling at 10 miles an hour. You have to get someplace 10 miles downstream. How long does it take you to do a round trip? You can't just subtract, add those together 15 miles an hour there and back. It's like, no, that doesn't work because when you come back, you're against the current. So you basically have to figure out time, right, is distance over velocity. Distance is 10 miles both ways, but the velocity is different. It's 15 miles an hour downstream, it's 5 miles an hour upstream. So you have to calculate the time upstream and then the time downstream. And add those together. You can't use the same speed. I think that's the end of chapter 2. Chapter 2 at the end does go over what are called problem-solving basics. I do recommend reviewing that before the final. Because again, these are the types of, that problem-solving basics are useful in all problems. Write down what you know, write down what they ask you to find. Do you have a relationship that deals with those things? All right. Then you have the free fall problems. Free fall problems are just these equations in the y direction, where the acceleration is minus 9.8 meters per second squared. When dealing with free fall problems or projectile motion problems in general, make sure you have the signs correct, right? If you define up to be positive and down to be negative, then any velocity that's going up is a positive velocity. Any velocity that's going down is a negative velocity. So for example, let's say I'm in a hot air balloon traveling down at 1.5 meters per second, and I drop a package off the end, and it falls, say, 100 meters, it hits the ground. And I want to know how long does that take? Well, write down what you know. What is the initial velocity of the package? It's not 0, it's 1.5, but what direction is it going? So it would be minus 1.5 meters per second, because it's going in the negative direction. Final velocity, we don't know. Displacement, we know it to be 100 meters. We don't know the time, that's what I want you to figure out. What's the last bit of information that we have? That's not explicitly given, but I told you it was a free fall problem. Gravity. What is the acceleration due to gravity? 9.8 meters per second squared, but what direction is it? Negative, it's downward. So you would plug all those into problem number 2 has everything, equation number 2 has everything we need, right? We could x minus x dot, we can move that to the displacement instead of y's. We know what the initial velocity is, and this has initial velocity. We know what the acceleration is, we can plug in that minus 9.8. So this is going to be a negative number. That's going to be a negative number. It's very useful and very important when solving, especially this equation for time. Note that's a quadratic. So you should have a calculator that has the quadratic formula plugged in, a way to solve the quadratic formula quickly. You don't want to have to go through the, okay, it's, what is it, plus or minus square root of b squared minus 4ac over 2a, right? You don't want to have to do that on paper during a test. If you have a calculator that can solve the quadratic formula, or you can program it in to do it quickly, if you add the coefficients a, b, c, and it'll tell you what the answers are, that's what you want to have available. I can't guarantee there's going to be one of these on there or not, just that quadratic formulas occur enough in physics problems that you should have a quick way to solve them. Questions on this? Goes on to graphical motion, which is similar to one-dimensional motion. That ends chapter 2. Chapter 3 talks about two-dimensional kinematics, so projectile motion, right? It starts dealing with vectors. You need to know how to break down vectors into components, right? So if I move 5 miles at an angle of 30 degrees above from east, right, or from the positive x-axis, what is the x component of that motion? What is the y component of that motion? You should be able to use your geometry skills, right, SOHCAHTOA, sine, cosine, tangent, to figure out right triangles. Right, that y will be the same as this y. It's a right triangle. So if I tell you what the x velocity is of an object, I tell you what the y velocity is of an object, you should be able to use Pythagorean theorem to tell me what the total velocity is of an object, right? At some instant, an object is moving 3 miles an hour horizontally and is going down 5 miles an hour, right? You should be able to figure out what the total velocity v is, its direction and magnitude, using, again, sines, cosines, tangents, and Pythagorean theorem. And your book goes through vector addition and subtraction at the beginning of chapter 3. And we had that lab on force table as well. So I won't dwell on vectors. Projectile motion, have a set of equations, a review of the kinematic equations, but what your book does is it plugs in, for projectile motion, it plugs in a bit of what we know. Like for instance, in the x direction, or horizontal, there's no acceleration. So you have v sub x is equal to v naught x. The velocity in the x direction always stays the same because the acceleration is 0. X is equal to x naught plus v naught x times t. And that's it, because the acceleration is 0. So these are your equations for the horizontal. For the vertical, it adds y instead of x because we're moving vertically. But then it also, so v sub y is equal to v naught y minus g times t. Rather than putting things in terms of a sub g, which is minus 9.8, they explicitly put the minus sign there and just add g, and g is always, in these equations, plus 9.8 meters per second squared. It's just the absolute value of the acceleration. The negative sign is explicit. This equation assumes up is positive and down is negative. And then you have y is y naught plus the initial v naught y times t minus 1/2 g t squared. Again, acceleration is downward with a magnitude of 9.8, and your book explicitly puts that in. And then finally, v squared is equal to v naught squared, or v naught y, minus 2g delta y. Be careful when using this, any version of this third equation, because it's the velocity is squared, which means that when you have to solve for v sub y, you're taking the square root. The square root of a number, square root of 9, is plus or minus 3. You'll have to look back at your problem and go, well, is the object going down or up? If the object is going up, it's a positive y velocity. If the object is going down, I have to add the negative sign to it. This top equation will give you a negative sign if it's going downward. The bottom equation will not. You will have to double check to see what direction it's going. Questions? Yes?
Can we skip ahead and talk about chapter 12?
Chapter 12? All right.
Yeah.
We'll jump ahead and then come back. Chapter 12. So fluid dynamics?
Yeah.
Okay. So talking about the flow rate.
Quick question,
Yes.
so I would square it first and then add the sign depending if it's up or down.
Well, when you take this, you would solve the right part of the equation. You plug in the initial y velocity, acceleration, displacement, and you would get a number out, and you would take the square root to get this final velocity. But you'd have to pause and go, wait, is it going up or is it going down? Because the square root of a number, the answer is always plus, or the square root of x squared is plus or minus x. And you have to determine, is it plus or is it minus? You have to think about, is the object going down? Then the answer will be negative. Is the object going up? Then the answer will be positive. The magnitude will be the same. Whereas in this top one, there's no square root that you have to worry about. If this is positive, you know it's going up. If this answer is negative, you know it's going down. So the flow rate for a fluid use Q, right? It's the volume of the fluid over how much time it takes to pass. So volume is units of meters cubed, and time is units of seconds. So this is meters cubed per second. So think of it like filling a swimming pool. How long would it take? Well, if you have a little garden hose, it would take a very long time to fill an Olympic-sized swimming pool because the flow rate would be small. But if you have a huge, large radius tube pumping out water at the same speed, you get a lot more volume out and the flow rate would be higher. Or think about draining a bathtub, right? I mean, it can't be the only one where, after a shower, hair clogs the drain, blocks part of the drain, it takes longer to drain, a bath or a shower. And if it's clean, then there's more area for the water to get through, the volume flow rate is higher, the bathtub or shower empties faster. So when talking about Bernoulli's principle, then what it states is if you restrict the flow of a fluid, you change that fluid because the flow rate has to be constant in a closed system. So if you have some kind of a hose that funnels down into a smaller area, right? The flow rate here, in this area we'll call it area 1, has to equal the flow rate in area 2. If it doesn't, what happens? Well, if Q1 is bigger than Q2, then water would build up here and magically get denser and denser and denser, and it doesn't do that. If Q1 is less than Q2, then a vacuum would form because you'd have more fluid leaving than coming in. You have this area of nothing, which can't happen. So these two things have to be the same. Another way of doing volume over time, right, meters cubed per second, what if we did cross-sectional area over velocity? So what ends up happening, or sorry, times velocity, my apologies, times velocity, not divided by. Cross-sectional area times velocity. Well, area is in meters squared, velocity is meters per second, so when you multiply these together, we get meters cubed per second, which is the same as the flow rate. So if we know what the cross-sectional area is, and we know what the area 1, and we know what velocity 1 here, if we know what the cross-sectional area, area 2 is, and we know the velocity, those have to be the same. Q1 has to equal Q2, so A1 V1 has to equal A2 V2. And you've probably all done this. If you've ever used a garden hose, you put your thumb over the end of the garden hose, what happens to the jet of water? Faster, right? It spits out a lot faster and a lot further. So again, if I know what the cross-sectional area of this tube is, it's usually, if we think of a circular tube, right, it's going to be pi r squared, where r is the radius of the tube. And then v is just the speed at which the water goes through. So rivers do this as well. If you've ever been tubing on a river or kayaking on a river, when the river is big and wide, it's very slow moving. And when it gets down to a narrow channel, that's where you get rapids, the river moves much faster. Questions on that? So Bernoulli's equation would be probably the next complicated one. There's a lot going on in Bernoulli's equation.
That's the one that I was gonna,
Okay.
I couldn't find.
That's a tough one. But just remember what Bernoulli's equation says is the pressure plus 1/2 the density of the object times the speed of the fluid squared. And we want to make sure the last one, plus 1/2 of the, or sorry, not 1/2, it's the density of fluid times g times the height of the fluid is equal to a constant. P is obviously deals with pressure. This kind of looks like kinetic energy, right? It's 1/2 the density times the speed squared. It's not the mass, but this is kind of kinetic energy. And this one is kind of potential energy, or gravitational potential energy. So Bernoulli's equation is kind of a conservation equation, where if you change one of these terms, the other terms have to change so it still equals the constant. If you increase the pressure, if this goes up, then either the velocity will have to decrease or the height will have to decrease in order to keep this constant. Or another way of saying it, decrease the height of the fluid, you increase the pressure. So Bernoulli's equation is often not written like this. What it'll be pressure at some point plus 1/2 the density times the velocity of the water at that point plus rho times g times the height of the water at that point will equal the pressure at some other point plus 1/2 the density of the fluid times the velocity at that second point plus m times g times the height of that second point. And with the Webb-assigned problem, I think what some people got mixed up with is in part B and C of that Webb-assigned problem, you had to, part B talked about, okay, we changed these things, on the equation, how does the other thing change? And then C asks, they change it again, but some people use the pressure they got from part B in the equation, but still using the velocity and the height they got from part A. You can't do that. Everything on one side of the equation has to be at the same moment in time. Whatever the pressure is at this instant or point in the fluid, the velocity at that point in the fluid, and the height at that point in the fluid, all have to occur at the same point in the fluid. Then if I change the height, I'm at a different height, I have to have either a different pressure or a different velocity or both. So one way to do it is to put in what you know. The problem, again, you have to convert everything to SI, so that means pressure has to be in pascals, not atmospheres. Velocity has to be meters per second, height has to be in seconds. G is 9.8 meters per second squared, you're fine with that. The density of the fluid has to be in kilograms per meter cubed. Right, everything has to be SI as you go through. Does that help with that a bit? Explanation?
At the end here, should that be density instead of mass?
Oh, sorry, yes, thank you. Yes, thank you. Again, I had the potential energy equation in my head, so it's the density of the fluid. So assuming the density of the fluid doesn't change, because density of water doesn't necessarily change. You can change it under incredible pressures, but we often think of fluids as incompressible, unlike gases. Fluids are often thought of as incompressible. That's why your circulatory system works, and why you don't want to inject a large air bubble into your bloodstream, right? Because if you inject a lot of air into your bloodstream, air is compressible. Your heart will try to compress down the fluid to push it through the system, and if that air bubble gets into your heart's like, compress, and the air's like, okay, and the blood's like, I don't feel any pressure to go anywhere, and your heart stops, and bad things happen. So, small air bubbles your system can accommodate for. Eventually, the air dissolves out of your system. The blood dissolves into the blood and then gets out through the lungs. But large air bubbles in your circulatory system, not a good thing. Large air bubbles in your brake system in your car, not a good thing. Large air bubbles in the power steering system of your car, not a good thing. So we typically think of fluids as incompressible. But the density, it might be brake fluid, it might be water. Typically these problems you do with water. And the neat thing is, even back 2,000 years in Greek and Roman times, they had a rough idea of this equation. Like the Hanging Gardens of Babylon, the famous wonder of the world, actually had a irrigation system where they bring in water from in one height, and they were able to actually put water throughout the gardens because they kind of knew how pressure worked at different when you change the height of the fluid. And this is why water towers are water towers, right? You pump the water up to a very high point, And then just the height difference of your house to the water tower gives you more pressure in your sink. That's why if you live on a hill, you might have crappy water pressure compared to someone who doesn't. And most hotels, beyond a certain point, you can't, well, I think it's about 30 feet, water can't get above there, so you have to pump it up. Questions? Other questions on this? Everyone happy with this? All right, that's still moving forward on 12. To do some Bernoulli's. And you can see that there are three kind of variables on either side, right? The density of the fluid will usually be given. G is always 9.8. So the variables are the velocity, the pressure, and the height. So usually what will happen is they'll give you two of them, right? Well, they'll say one stays constant, and then they'll change one and ask you how the other one changes. Or they'll say, oh, we changed the pressure. We changed the pressure to this and the height to that. What's the new speed? You really can only solve for one unknown in this equation, right? You only have one equation. So either something's going to be constant and you don't have to worry about it, like if the velocity is constant, then it's the same on both sides and drops out of the equation. Or they'll give you everything but one thing and then you can solve for the other one. So applications of Bernoulli's, how dams work, how water towers work. Viscosity and laminar flow, we really didn't, I'm not going to worry about that. Don't worry about viscosity and laminar flow, I'm not going to quiz you on that. But that's a bit too complex for this level of physics in my opinion. And again, all the constants of viscosity, since we're not going to deal with it, you don't have to worry about it. Motion of an object in a viscous fluid, I'm not going to worry about that. So that basically ends 12. Any other questions about 12?
Is one of these going to be on the test?
It's possible. It's certainly possible. It would be in the final, not on because the exam 3 starts with thermodynamics, so not fluids. But on the final exam, it's certainly possible. But it won't be as complex as the homework problems, right? I'm not going to ask you many multi-step problems on the exam. It's going to be mainly 1 or 2 step equations. Like projectile motion one, you might have to solve for the time it's in the air, solving the y equations, and then once you know the time, plug it into the x equations to get the distances traveled horizontally. You know, those 2-step problems. And then some unit conversion that you have to worry about. I'm not going to do any problems that will take you, if you know how to do them, they should take you a minute or two to plug out and move on. If you're struggling a little bit or you're trying to remember, maybe 4 or 5 minutes for a problem, I'm not going to set up a problem that will take you 15 minutes to do if you know what you're doing. Right, everyone's happy with 12. We're going to jump back to 3 and 4 quickly. So problem solving kinetics of falling objects, we had those equations. The 3 vectors we talked about, projectile motion. So jumping to chapter 4. Chapter 4, we start talking about the laws of motion. Newton's first, second, and third law. So the thing about this is it's important to be able to set up, draw a free body diagram, and set up these types of problems. Like, let's do an example. You have an elevator. Right? That weighs 1,000 kilograms. That has a cable. That cable snapped, but at the last second, Superman sweeps in and has a force upward of 8,000 newtons. what's the acceleration of this elevator? Is it 0? Does Superman, does he just hold it still? Does it accelerate upward? Does it accelerate downward? What is the acceleration? Newton's second law states the net force, F net, is equal to the mass of the object times the acceleration of the object. We need to find out what the net forces are. The net force is the combination of all the forces on the object in that direction. We're just talking about y motion here, fortunately, right? There are no x forces here. There's nothing pulling it side to side. So just drawing a free body diagram, here's the elevator. What forces are acting on the elevator?
Is gravity?
Gravity is absolutely pulling down.
Then you have the force normal pointing upward perpendicular to the surface of.
Force normal would be there if it were pressing on a surface.
Oh, okay.
But the elevator is just floating in space.
You have Superman pulling it up.
You have Superman pulling it up. Force of Superman. And that's basically it. Those are the two forces. Now, normal force, you're absolutely correct. And those forces you have to worry about on like inclined plane problems. Right? Gravity will be pulling down. Normal force will be going perpendicular to the surface. But that's only if the object is resting on a surface. Like right now, there's a normal force on all of you, right? The chair's pushing up on your butts, right? That's the normal force. The floor is pushing up on my feet. If I lean against the wall is pushing back on me. If it wasn't, I'd go right through the wall, right? I'm pushing on the wall has to push back on me. So these are the only two forces. We're going to define up to be positive and down to be negative. So we have the force of Superman in the positive direction minus the force of gravity. It's minus because it's acting in the negative direction. Is equal to the mass of the object times the object's acceleration. Well, I know the force of Superman. I'm giving it to you. 8,000 newtons. What's the force of gravity? How do we figure that out?
Mass times gravity.
Mass times gravity. Yep. M times G. So the mass, which is 1,000 kilograms, I should be able to do that, 1,000 kilograms times 9.8 meters per second squared, is equal to the mass, which is 1,000 kilograms, times the acceleration. Now, if you plug this in, you'll find that 1,000 times 9.8 is 9,800, or sorry, 9,800. So it's 8,000 newtons minus 9,800 newtons, which is equal to 1,000 kilograms times A. So that's minus 1,800 newtons is equal to 1,000 kilograms times the acceleration, divide both sides by 1,000, minus 1.80, right, is equal to acceleration. It's newtons over kilograms. Newtons divided by kilograms. But what is a newton divided by kilogram? What is a unit for acceleration?
Meters per second squared.
Meters per second squared. Is equal to the acceleration. I'll prove it to you. A newton is a kilogram meter per second squared divided by a kilogram. Kilograms cancel, leaving you with meters per second squared. So in these free body diagrams, when you're calculating forces, to get the accelerations, you have to identify all the forces, identify what direction there are, positive or negative, and the acceleration, our result, is negative. So what does that mean? Is the elevator going to be going up or down? Down. It'll accelerate downward. I didn't say what the initial velocity was. Maybe it was traveling upward, or maybe it was stationary when the cable broke or whatever. The acceleration downward means that eventually Superman is basically lowering the elevator gently, hopefully, to the ground. Friend sent a website to me a couple months ago. Apologize for the language. It's called superdickery.com. It's basically showing old covers of old Superman and how awful Superman was to everyone around him. It's like, oh no, I'm going to have to erase Lois's memory again. Or I can't let Jimmy Olsen deposit that money in the bank. It's run by, So it's just like him being awful to all of his friends. It's hilarious. 1950s comic books are just brilliant. Let's see. how many times Superman has had to trick Lois into marrying other people so she wouldn't find out his secret. It's hilarious. All right, moving on. So the forces we have to deal with, right? Tension forces, right? That's a pull from a rope or cable. You have the normal force, which is always perpendicular to a surface. Gravity, which unless your problem is in space, it's, unless you're away from any planet, is always going to be an issue. And that's always pulling, I don't want to say down, but it's always pulling towards the Earth. It depends on how you define your coordinate system. And we'll talk about another force, friction, in a bit. And then there's just the regular pushes and pulls, right? You can go up to a box and push on it or pull on it. Those are forces that can act on objects. So read through the problem solving in chapter 4 on the stages on how to set up a problem. That's very useful. And look at the example problems that they address. Good question.
Yeah, so I'm sure we'll talk about it in a little bit, but what's the equation for figuring out tension?
There is no equation for tension except that you have to set up your X and Y Newton's second law forces. So, like, for example, if I have two cables supporting a box, right? So let's say this cable is at 30 degrees, this cable is at 50 degrees. And it's supporting that box. Let's put it right on the box instead of having a cable down like that, right on the box. So what forces, that box is hanging from those two cables, what forces are acting on the box?
Gravity.
Gravity's absolutely pulling down on it. But if that's the only force, it's just going to fall. They're tension, right? There are two cables, so there are two tensions. We'll call the left one tension 1, T1, and the right one tension 2. But note now, this is no longer a one-dimensional problem. It's a two-dimensional problem, right? There are X components to these forces, and there are Y components to these forces. That mass is not accelerating. It's stationary, which means that all of the forces in the X direction, mass times X acceleration, is going to be equal to 0. It's an equilibrium. And all the forces in the Y direction also equal 0 because it's not accelerating downward. Okay, what forces, let's look at the X forces first. Which of these three forces, or do they all have components in the X direction? They have some horizontal part to their force. The tensions, left and right, what about gravity? Gravity's down, right? It has no horizontal component. So the net forces, if I define the right to be positive, the X component of tension to the right minus the Y component, or the X component, sorry, of tension to the left is equal to 0. Or T2X has to be equal to T1X. And hopefully that makes sense, right? The pull to the right here has to be the same as the pull to the left there. Otherwise, that box would accelerate one direction or the other. I don't know what those tensions are, though. I just know that they are equal to one another. Now, the Y forces, T1Y is in the positive direction, plus T2Y is in the positive direction, minus the force of gravity is equal to 0. Well, I can give you if I give you the mass of the object, say the mass is 100 kilograms. You can figure out F sub g, right? It's just 100 kilograms times 9.8. Well, what about X? We have 4 variables there. We have T2X, T1X, T1Y, T2Y. So I can't solve those two equations right now because there are too many unknowns. But I can use geometry to figure out the X component, right? This is 50 degrees, alternate material angles are congruent. It's 50 degrees. sub y for T1. This is T1x. So T1x is equal to T1 times the sine of 50 degrees. T1y is equal to T1 times the cosine of 50 degrees. So I took those two variables and turned it into one. I just need to know what T1 is. And then T2, I can do the same thing. T2x is equal to T2 times, with the x component, that's 30 degrees, so sine of 30 degrees. And T2y is equal to T2 times the cosine of 30 degrees. So if I plug these into here, I end up with two equations and two unknowns. The only thing I don't know is T1 and T2, and I can solve one of the equations for T1, plug it into the other equation, and just get an equation for T2, solve that, and then go back to solve for T1. If you have two equations and two unknowns, that's a solvable system. A little complex for an exam, right? Because I'm not going to have, you're not going to have that much time to go through this problem. But that's, so there is no real equation for tension. You find that by setting up the Newton's second law equations. Whereas gravity is just mass times g.
Thank you.
Yep. Or I could have done the Superman one backwards, where I say, how high, what's the tension force necessary for Superman to have an acceleration in the negative direction of 1.8? Then you would set up the same equation, except instead of solving for acceleration, you'd solve for tension. And then the whole chapter 4.6 deals with problem-solving strategies, how to set up free body diagrams. And those are, most free body diagrams are common, you know, a bunch of kids are pulling on this sled in this direction. What's the net acceleration and net force? An elevator is being pulled up or down, or a one of those wrecking balls is being pulled up or pulled down by a cable, that sort of thing. So they seem to have similar types of setups. Box is sliding down a frictionless plane, or even on a frictionless plane, it might have friction on it. But a box on an inclined plane is a pretty common result. Frictional forces. Chapter 5 deals with more forces, but more complex forces. Friction is one of those forces. So you have an inclined plane where you just have a box of mass m, and that's all you have. There are no other forces acting on it, right? Gravity's pulling down. There's some component of gravity in the x direction. That's from gx. I define my plane down as positive, up as negative. So depending on the angle of the inclined plane theta, I can figure out the acceleration due to gravity. Normal force is always perpendicular to the surface. Frictional force, static friction or kinetic friction, depending on if it's moving or not, is always parallel to the surface. It's along the surface. And it's always trying to resist motion, right? Friction, if I try to push this little box to the left, friction is holding it, is fighting me pushing to the right. When I stop pushing, friction stops too. If it didn't, there'd be a force, unbalanced force to the right, and this thing, friction would just pull this thing off to the side, and it doesn't do that. So to figure out this friction, specifically the maximum possible static friction, you have to know what the coefficient of static friction is. That is a unitless term that depends on the surfaces in contact. The smaller mu sub s, the slipperier the surfaces. And then you need to know what the normal force is. That's how hard are the forces, how hard are the surfaces pushing on one another. If you've ever moved a couch on a carpet, push it and it doesn't move, one way to start it moving is to lift up on it too. Right? mean, if you could lift the entire couch, it would be easy to move. But you can't, so you just lift it up a part of it, or lift it up enough that the normal force is less, so the frictional force is less, so it's easier to slide. mu sub k is the force for kinetic friction, which is mu sub k also times the normal force. You can only use one of these at a time. Either the object is moving, in which case there's static friction, or the object is not moving, in which case it's moving, in which case there's kinetic friction, or it's not moving, in which case it's static friction. You can't use both frictions in the same environment, right? It's one or the other. Either this is stationary up here because it's being held by static friction, or it's sliding down and kinetic friction is trying to slow it down. It has to be one or the other, it can't be both.
And just to be clear, like mu sub s or mu sub k, we're either going to be given that value or we're solving for that value.
Yes, because that completely depends on the surfaces in contact. That's not a number, that's not even a number I can think of at the top of my head off two surfaces, right? That's experimentally, you really have to play around with that, to do the experiment to measure that. So either give it to you or you have to solve for it. And it is unitless. Because that's a force, that's a force. This has to be, if this is any unit at all, then this would not equal one another. So they are unitless. Typically less than one, but not always. The drag forces. Drag forces are tricky because they vary with speed, so they're not constant acceleration forces. So F sub d is 1/2. I want to make sure I use the same value as your book. Some coefficient times the density of air times the cross-sectional area times v squared. Where c is just some drag coefficient. Rho is the density of the fluid that you're moving through, the density of air. A is cross-sectional area. Right, think about it in terms of skydiving, right? Why do you have a parachute? Because you make the cross-sectional area very big, which slows you down because it provides a much bigger drag force. And then v squared is the speed that you're traveling at. So the faster you're traveling, the bigger the drag force. And all of you probably experienced that. You'll stick your hand out of a car window as a kid. When you're on the highway, you can feel the air pushing on your hand. You do that when you're in the city, not nearly as much. Or we're stationary, there's no real force at all. Drag coefficient, again, is the relationship between how the material interacts with the air around it. So in a swimming scenario, right there for a while, they had the shark suits during the Olympics. It was supposed to decrease the coefficient, drag coefficient, so it makes the bodies easier to flow through the water. Or why swimmers shave their legs, typically, shave legs and arms, because they think that that makes them swim faster. I'm not sure if there's science supporting that, but they do it. So another one's holding the gold medal record, so I'll just believe them. So that is not something you can know. That's something that has to be given or you'd solve for. It's also why your car has the top speed, right? Your car engine produces a force to push you forward. The faster you go, the bigger the drag force, until eventually the drag force equals the force that your car can put out and you reach your car's top speed. We dealt with stress and strain, Young's modulus. We actually covered that in a slightly later chapter with 9, but it's at the end of 5. I thought it worked better with stress and strain. So the change in length of an object, if you're putting a tension on it, is 1 over y, which is a coefficient called Young's modulus. The force applied over the cross-sectional area times the original length. So for example, that string that's dangling down right here, if I place a force at the end of it, the string has a cross-sectional area. It's not a super thick string, but it's also not as thin as the little string hanging next to it. If I know what that cross-sectional area is and I knew what the Young's modulus was of the string, I could tell you how much the string is stretched when given that force. Eventually, an object will bypass what's called the elastic limit, will bend or break or shatter, and will be no more good as something to support weight or hold force. Concrete columns do this, buildings do this, right? When you have a big I-beam or a big like Roman stone column or Stonehenge, if you place another stone on top of a weight, you compress it by some amount. How much you compress it depends on, again, the force that you're applying, the cross-sectional area of the object you're pulling or compressing, and Young's modulus. Young's modulus depends on the material. And that's something, again, that I will give you. Shear deformation is actually almost exactly the same equation. Shear just means perpendicular force compared to compression or a pull or push. So imagine you have a flagpole with some cross-sectional area A, and you place a weight or mass on it that would apply force downward. The pole will bend downward. Right? Simple version of that, oh, of course I don't know. The 2 meter sticks we have, right? Under their own weight, they deform downward. If you hold them out. So the amount of displacement, delta x, how much does it bend down, is 1 over the shear modulus, instead of Young's modulus, because some materials are great in compression but suck in shear forces. Concrete's one of them. F over A, cross-sectional area, times element. That's why those big bridges, concrete, like bridges that span, are reinforced concrete. There's usually rebar or something, some metal in there to help the concrete support the weight. If you go to actually ancient Roman structures or structures of the ancient world, there are a lot of vertical columns because you can't have very much horizontal concrete blocks before the blocks start to break under their own weight from the shear force. So you have to support them with a lot of closely spaced vertical columns.
What did you say the very last was?
I'm sorry? S is the shear modulus. Again, it's something that's material dependent. How good is how bendable basically is the material, if you want to think of it that way. Like the wood would be very bendable. It would have a very small shear modulus, which would give you a big X displacement as you place the force at the end. Whereas a steel rod, oh, here's a piece of wood, right? I think someone tested the shear modulus on this a little too much, but you push down, right, it bends. But if this were a steel rod, it would be harder. And the fatter, the thicker the cross-sectional area, the less it's going to bend. And that's in chapter 5. Chapter 6, we talked about uniform circular motion and centripetal motion. So for this, just remember that the equations for rotational motion are almost identical to the equations for linear motion. Just the variables differ, right? So for rotational motion, position is x, but for angular motion, so this is linear versus rotational. For linear, rotational, it's theta. Velocity is v for linear, it's omega for rotational. Acceleration is a for linear, it's alpha for rotational. So all of the equations that we had for linear motion, you could have for rotational motion. So the three major equations, right? You have theta is equal to theta naught plus omega naught times t plus 1/2 angular acceleration t squared. Exact same equation for linear motion, they just replace them with their rotational analogs. Omega is equal to omega naught plus alpha times t, or omega squared is equal to omega naught squared plus 2 alpha times delta theta. So the same relationships apply, except that now we're dealing with rotational motion, where this is the original position, angular position, versus the final angular position. This is the angular velocity, initial, final angular velocity, and the angular acceleration. And time is still time. Units, instead of meters per second for theta, right? So units here are meters per second. Here the units are radians per second. Sorry, meters and radians. Meters and radians, and meters per second and radians per second. Acceleration meters per second squared, for angular acceleration radians per second squared, and so on. So how a radian establishes with a degree, you should know that. There is a relationship if you have rotational motion, like a spinning wheel. You have a wheel of some radius, you have a particle on that wheel. Its linear velocity is related to the angular velocity of the object, where the linear velocity is just r times the angular velocity. So this is radians per second times meters, so you end up with meters per second.
Just a question, like how we did the linear equation before when it was v squared and now we have omega squared. Is it still, like, if we just want to find out what a single omega is, we have to figure out?
Well, you have to find the direction of omega. So
Yeah.
counterclockwise motion is positive. Clockwise motion is negative. So if you did the square root of omega squared, you'd have to go, oh wait, was it rotating clockwise or was it rotating counterclockwise? And that would tell you if it's a positive omega or a negative. Then we moved on to talk about centripetal acceleration and uniform circular motion. Centripetal just means inward, center seeking. So imagine a person standing on the edge of a merry-go-round, some radius r, we're looking down on them, right? And the merry-go-round is rotating with some angular frequency omega. The only way that can happen is that if there's an inward force, a centripetal force, holding that person on the merry-go-round. Same thing, imagine a bucket with a rope around your head. Grab the bucket, start spinning it around. That bucket is moving around you because of the tension force pulling that bucket inward, a centripetal force. If you cut the rope, the bucket won't go around you anymore, it just flies off. That's one of the things, if you ever watch sci-fi shows, I just watched Cloverfield Paradoxes on Netflix. One of the things that I saw, the physics that bothered me, was their space station, which is spinning, blew up, part of it blew up, and there's a debris field. But the debris field spun around with the space station, like it was just glued to it somehow. It's like, no, that debris would just fly off in a straight line. There's nothing holding it to the space station anymore. So the centripetal force is equal to the mass times the centripetal acceleration. But for uniform circular motion, the centripetal acceleration is the speed of the object over the radius. So this object is going to have some speeds, some velocity v, some magnitude of that velocity is speed, at some distance r. So, for example, if I know what the velocity, the speed of the Earth is around the sun, and I know the distance between the sun and the Earth, I can calculate what the centripetal acceleration is of the Earth. If I know the mass of the Earth, I can calculate the force of gravity on the sun. Or vice versa. If I know what the force of gravity is, and I know the mass of the Earth, I can calculate the centripetal acceleration. If I know the radius of Earth's orbit, I can tell you how fast Earth is going around the sun right now. 90 miles a second, approximately, actually. We're going around the sun at about 90 miles a second. So this is useful, I think, we've had equations, homework equations dealing with centrifuges, right? In biology, one way to separate out, like, plasma. If you do plasma donations, they take your blood. They don't actually cell by cell pull out all the red blood cells and put them back into you, right? They have to separate them out somehow. So they put your blood in a centrifuge, spin it around at a high rate of speed. High velocity, this also, again, using the equation over there, the relationship, this is the same as omega squared times r. So a small radius centrifuge spinning at a high rate of speed gives you a very high angular acceleration, which gives you a very high force. So you can mimic high gravity, very high G forces, which then pull the platelets and stuff, the blood out of the plasma. They then scoop off, they keep the plasma and then direct the rest back into you. Or plasma donations. You just don't need blood to keep it all. But plasma, blood, I forget exactly how long it takes to recover from blood donations. It's a few days at least. I think a few weeks before all your blood cells are back up. Red blood cells are back up. Whereas plasma donations, I think it's just a day or two before you're basically recovered. Because it's just the fluid and not the red blood cells. But I'm not a biologist, so I'm going off of what I remember from friends who donated. Question, yes?
I was just wondering, is this partly recorded too?
Yes.
Okay, and will you send that to us tonight?
I will compress it and send you the link on YouTube tonight. So again, if you have to go, it's 4 o'clock, it's getting late. I completely understand.
Alright, thank you.
But I will keep on lecturing as long as people are sitting here. So. But yeah, I will send up, I might have to break it up into smaller videos,
Okay.
but I will definitely put it up all on YouTube tonight.
Alright, thank you.
So, dealing with centripetal forces, you might get something like a centrifuge that's 0.5 meter in radius, is moving around at 1,000 RPM. What's the force, or what's the centripetal acceleration of this object? Well, 1,000 RPM would be omega, that's the rotational speed, but that's in rotations per minute. Omega has to be in radians per second. So you have to convert RPM into radians per second. And for rotational motion, that's probably the most common conversion you'll be doing. Because RPM is typically, again, if you have a engine gauge on your car, if you drive stick or some automatics have it, it tells you what the RPM of your engine is. Rotations per minute is a typical way of talking about rotational speeds. So it goes from rotational motion that jumps into Newton's law of gravity. Gravity is also a centripetal force, kind of, for the planets. The planets don't have perfectly circular orbits, but we can pretend that they do for the purposes of this class. So Newton's law of gravity states the gravitational force is equal to some gravitational constant, which is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. So the product of the masses of the object over the distance between the center of those masses squared. And that's where Newton's breakthrough actually occurred, is that he realized that gravity acts as if it's coming from the center. This distance from the center of the Earth matters, not your distance from the Earth, right? We're standing on the Earth now. But if you go to the space station 250 miles overhead, the distance from the Earth is not 250 miles, it's 250 miles plus the radius of the Earth. If you know the radius of the body, let's say the radius of the moon, you know the mass of the moon, you know your mass, you can calculate out what the force is on your body on the moon. Gravity exists everywhere. You will always notice it's if the distance is squared, it weakens quickly as you get further away from an object, but it never really goes to zero. So in the International Space Station, they're still being pulled around the Earth by gravity. If they weren't, they'd fly off in a straight line. Orbits are objects that are being pulled on by Earth's gravity. Now, all of the gravity forces going to the rotation of the object, the space station is also experiencing the same force, so there's no normal force because the space station isn't pushing on you, you're not really pushing on the space station, you're both in free fall. So even though they call it microgravity, but in reality, the gravitational force at that distance isn't much different than it is here. The only difference is they're constantly falling. That's what an orbit is. There's an old book called The Hitchhiker's Guide to the Galaxy, which has the comic portion saying, if you want to learn how to fly, it's easy. Just throw yourself at the Earth and miss. But in reality, that's what space stations do. That's what satellites do. We launch them with such a high horizontal velocity that they're constantly falling, but as they fall, they're moving horizontally so much the Earth is curving away from them, so they're just falling around the Earth. And that's what an orbit is. So talk about Earth's gravity, the centripetal force. They talk about microgravity in your book. Kepler's laws. We're really not going to stress Kepler's laws on the exam, so you don't have to worry about that. Just one little section. That's chapter 6. Then chapter 7 begins talking about energy, I believe. Work, energy, and resources. So remembering, work is force times distance. Force in the x direction times the x displacement is work done in that x direction, right? So force times distance. A force has to be applied through a distance to do work on an object. If that object isn't moving, if there's no displacement, no work is being done, right? I can push on this wall until I'm blue in the face with all the force I have to muster, but this wall is not going to move, therefore I did no work on it. When you do work on an object, you change that object's kinetic energy. There's the work kinetic energy theorem, where kinetic energy is equal to 1/2 the mass of the object times the speed of the object squared. Hopefully all of you have that burned into your head. We've used it quite often. So when positive work is being done on an object, the object accelerates because force is being applied over some distance. That acceleration leads to a change in velocity. Velocity, if you increase velocity, you increase the kinetic energy. So work, positive work, increases the kinetic energy. So if I drop this piece of chalk, it will go down through this distance, displacement, in the direction of the force. It will accelerate, picking up kinetic energy. Positive work is being done. If I throw this piece of chalk up, the force is down, my displacement is up, I'm doing negative work, it's slowed down. Kinetic energy is the energy of motion. It is a scalar, it is not a vector. It does not matter the direction of the object, it just matters the object's speed. Other types of energy, potential energy. Is your book PE or U? I always forget.
It's PE.
PE, okay. Usually it's U, so if I use that in class before, I apologize. Potential energy is the energy, well, it's potential, it's the ability to do work. So gravitational potential energy is equal to the mass of the object times the acceleration due to gravity times the height of the object above some reference point. So if you lift an object 10 meters, you can calculate how much gravitational potential energy that object gained. There's spring potential energy, which we already talked about, 1/2 the spring constant times the displacement of the spring squared. You can also have spring potential energy in winding a watch. If you have like this old school pocket watches or old watch that you wound, you're basically coiling up a spring, storing energy, and that energy is released through the watch mechanism to kinetic energy, causing the watch to move. Or gravitational potential energy. If you have a grandfather clock, right? You're pulling a mass, you're lifting a mass up. As that mass descends slowly, it causes the clock to move. So you're changing one energy to another. So if you have, for example, the roller coaster cart problem, if you know the height, let's say the zero height here, of a roller coaster, if you know the mass of it, we don't even need to know the mass because the mass can fall out in some of these equations. As this roller coaster descends, as its height's changing, gravitational potential energy is becoming kinetic energy. So one of the advantages of working with energy rather than forces is you can simplify some of these problems. If you had to solve this with forces, you'd have to figure out as a function of position the force vector, how much of it is in the x direction, and then you can calculate the velocity in that direction, and it becomes actually quite a difficult problem even with calculus. But with energy, it becomes super simple. Calculate the difference in energy, potential energy between 2 points. That has to have gone into kinetic energy, so you can talk about the change in kinetic energy between those 2 points. How much faster, how much slower did the roller coaster cart get?
And what's the relation between kinetic energy and potential energy again?
It's the total energy of the system and conservation of energy has to be constant. So the kinetic energy at some point plus the gravitational potential energy at that point, plus the spring potential energy, if there's a spring involved at that point, has to be equal to the kinetic energy at some other point, plus the potential energy, gravitational at that point, plus the spring potential energy at that point. And kind of like Bernoulli's equation, right? Think about what we did with the cart yesterday for conservation of energy. You stored energy in that compressed spring. So all the energy initially was in the spring. So the initial kinetic energy, the gravitational potential energy initially were 0. If you count the starting point of the car as a height of 0. You then pulled the pin, the cart went up the ramp. As the cart went up the ramp, spring potential energy, after it left the spring, all the spring potential energy was gone. So all the energy would have had to have been in gravitational potential, which was increasing as it went up the ramp, and kinetic. When it finally reached the very top of its motion, how much energy was in the spring? 0. How much energy was in kinetic? 0. So all of it was in gravitational potential.
Got it.
Ideally, of course, we lost a little due to friction, but we're going to pretend friction doesn't exist for these problems for now. That says, your book talks about conservative forces. This only works with conservative forces. Non-conservative forces, there'll be some, over here on the right, there'll be some energy term plus U, let's say it used to be, or that's thermal energy, or E-therm or something like that. I forget what your book calls it, where some of the energy might be there. So if I tell you between these 2 points that 10 joules of energy was lost to heat, you would just put 10 joules here and then figure out what's left for the other bits. And your book goes into conservation of energy, power. Power is just how quickly do you do work, right? Think of power lifters, right? What does a power lifter do? They take a weight on the floor, right? Give it a large amount of gravitational potential energy and then put it back down. The bigger the power lifter, the more power the lifter has, the faster they can do that. There's a great MIT experiment where a bunch of MIT students took a old cell phone with a vibrator, right? A buzzer. Inside it's a little motor that shakes the phone back and forth to vibrate. They were able to lift a fridge with that little motor. It took a long time to do it because there's not much power in that little motor, but they were able to get it done. So the power is just the work done over how much time it takes to do the work. And the units for power are watts, for SI units. So a 100-watt light bulb produces 100 watts of power. It's just that most of that power is given off as thermal energy and light. But your microwave, you might have a 1700-watt microwave or a 1200-watt microwave. That tells you how much power your microwave can give off at any unit of time. So it's work per unit time or sometimes energy per unit time, which means energy is equal to power times time. So this is where the kilowatt hour comes in if you have an electric bill. If you look at an electric bill, it says, oh, you use this many kilowatt hours. And you're like, that's the stupidest unit ever. Why would you measure things in kilowatt hours? Well, power is measured in watts or kilowatts as a unit of power, and hour is a unit of time. So a kilowatt hour is a unit of energy. They could just say you use this many joules, but most people don't know what the heck a joule is. So kilowatt hour basically is like 1 kilowatt hour is running 1,000 kilowatts for an hour. It's running 10 100 watt light bulbs for an hour.
So I don't know if I missed this, but what did we say the unit was for work?
Work is the same as joule, same as energy.
Okay.
So watt is a joule per second. Because if you think about it, work is the change in kinetic energy, so these have to have the same units. They both have joules. Again, power is just how quickly things are done. Power consumption, work and energy, world energy use. That's just interesting chapter about equations or any. And then moves on to chapter, where are we? 8, momentum. So, momentum, unlike energy, is a vector. P is equal to m times v, but it matters what direction the velocity is in. So it is a vector. Momentum, we used quite a bit when we talked about conservation of momentum. In collisions. When two objects collide, their momentum is conserved in that collision. So momentum of object 1 plus the momentum of object 2 initial before the collision is equal to the momentum of object 1 final plus the momentum of object 2 final. And your homework problems you used to have a ball runs into a stationary ball and bounces off of it, or something along those lines. So M1V1 initial plus M2V2 initial equal to M1V1 final plus M2V2 final. This holds for all collisions. All collisions, momentum is conserved. But there are different types of collisions. There are elastic, perfectly elastic collisions. And then there are perfectly inelastic collisions, and then there are just inelastic collisions between those. So we'll talk about elastic collisions. For elastic collisions, kinetic energy is also conserved. So 1/2 M1V1 initial squared plus 1/2 M2V2 initial squared is equal to 1/2 M1V1 final squared plus 1/2 M2V2 final squared. Kinetic energy of both objects before is equal to kinetic energy of both objects after. Think about elastic collisions like a Super Bowl, right? Bouncy. Atoms collide elastically. But in real collisions, usually they're not elastic because part of the material deforms. Like a car accident, right? The car deforms. Cars don't bounce off of, or at least usually not, right? If you hit another car, the car doesn't stay absolutely perfectly created and bounce off that other car. It wrecks. If it really wrecks and sticks to the other car that you hit, or if two objects that collide stick together, that's called a completely inelastic collision. Kinetic energy, any type of inelastic collision, kinetic energy is not conserved. In a completely inelastic collision, what that means is V1 final is equal to V2 final, which we'll just call V final. Objects stick together. After the collision. That's a completely inelastic collision. And that's usually a lot of problems with collisions are completely inelastic because that's one less variable I have to give you, right? I say, this object with this velocity and mass collides with that object with that velocity and mass. What's the final velocity if they stick together? That's a one problem. If it's a completely inelastic collision, then I can say, oh, object 1 has a velocity of this. What's object 2's velocity? You can figure that out a little bit. You have two equations and two unknowns. But for an exam, it's unlikely I'll give you that type of a problem because that's mathematically very difficult to work out. A lot of algebra.
We're going to have a lot of inelastic collision problems.
Inelastic collisions, or I'll give you the velocity of one of the objects and ask you to find the final velocity of the other. It'll be a one-step type of a problem. But it's important to know what elastic collisions are because I'm not just asking you numbers problems, I'm also asking you conceptual problems. So we talk about, we should do collisions, 1 dimension, 2 dimensions. Collisions our momentum is conserved in a dimension, so the y momentum is conserved, the x momentum is conserved. So you have two different equations if you want to know what's going on in 2 dimensions. Number 9, we start dealing with statics and torque. So statics is very much like chapter 4 and 5 where you're creating the free body diagrams, where you have the elevator suspended by a cable. The only thing about statics is that you know the accelerations are 0. So F net x is equal to 0, and F net y equal to 0, because it's static, the objects aren't moving. So there's no acceleration. So this will be things like I drew before, the box suspended by 2 wires. You know, that is a type of statics. Or Superman holding the cable was not a statics because the elevator was accelerating, but if I said Superman catches the elevator, how much force does he have to apply so the elevator is stationary? That's a statics problem. And you would say, oh, it's stationary, so the acceleration is 0, and then I can solve for the rest. And one last thing, torques have to be 0. So for statics, the torque is also 0. Torques, we introduced in this chapter, is a force applied to some perpendicular distance, right? So like a door looking above, here's the hinge, right? You apply a force when you open a door, you know what the radius is. If you know the door, let's say, is ½ a meter across, actually probably more than that, and the force is, say, 10 newtons, then you can figure out what the torque is. In this case, it would be 5 Newton meters. Units for torque are Newton meters. They are not joules. A Newton meter is a joule when you're talking about energy. When you're talking about torque, it's not a joule is not a unit of torque. A Newton meter is. And there are plenty of examples of these conditions, equilibrium conditions, in your textbook, for example, so if you want to look at that.
We had an example with torques and statics in the homework that had to do with a horse leaning against the wall.
Oh, yeah.
Is that going to be beyond the scope of what's on?
A bit. One thing might be something along the lines of there's a ladder hanging over the edge of a cliff. How far can you go up before the ladder tips? Okay. That's a common one, or some kind of a platform. So you have some ladder. Actually, it wouldn't be that long because it would tip over by itself. Right. Some mass here. How far can you walk out before it starts to tip? And then basically you would just find, okay, here's the center of gravity, right? There's a pivot point. How far can I go out where my force of gravity pushing down on this causes it to pass the center of the board, or past the point where the board is touching the wall. So that's type of a statics problem.
Can we work out an example
Sure.
like that? This is one area where I really struggle with.
Okay, let's actually do that example. We'll just put numbers on it. So we have a board. Let's say the board is 3 meters across, 3 meter long board that's sticking 1 meter over the edge of a cliff. This whole thing is 3 meters. And let's say it weighs 10 kilograms. Mass of the board is 10 kilograms. Someone walks out, a person walks out. How far can they walk out on the board? So standing on the board, imagine them on the board here. How far can they walk out before the board tips over? Before it starts to go over the edge. So how far from the cliff we're interested in. So we'll call that X. So this is an equilibrium problem where basically the board has the mass through its center of gravity, the middle of the board, and is down, right? I'm going to pick a rotation point. I'm going to pick the edge of the cliff as the rotation point. And then the person is to the right of that. So the torques have to be equal to 0. If the torque would cause a counterclockwise rotation, it's a positive torque. So if this is my pivot point here, and I'm looking at the board center of gravity there, if the board could, if the cliff wasn't stopping it, and I put a pin in here, would the board want to rotate counterclockwise, or would it want to rotate clockwise around that pivot point? Definitely counterclockwise. So that's going to create a positive torque. So the torque from the board around the pivot point is the force of the board, which is just the board gravity, right, from the board, times the distance from the pivot point. Well, if this is a 3 meter board and 1 meter is hanging over the edge, how far is the center of gravity? How far is the center of the board from that pivot point? Right, so if this is a 3 meter board, there's 1.5 meters on either side of the center of gravity.
Half a meter.
It's half a meter, because there's 1 meter here, so you only have half a meter left. So the distance here for the board is half a meter. So coming up here, tau for the board is equal to the weight of the board. The weight was, board is 10 kilograms. So 10 kilograms times 9.8 meters per second squared, because it's acceleration due to gravity, times half a meter. That's the torque from the board. Now let's just pretend this is 10. 10 times 10.5, this is about 48 Newton times meters. All right, happy with that?
Yep.
So, okay. That has to balance the torque from the person. And the person, that's the person, let's say they're 50 kilograms. Well, the torque from the person is going to be equal to the mass of the person, which is 50 kilograms, times 9.8 meters per second squared, because it's gravity, right? That's the force of gravity, times x, where x is the distance to the right of that pivot point. That has to equal the torque of the board for it to be balanced, 48 Newton meters. I have everything here I can solve for x. Right, so approximately, again, approximating 50 and 50 is about the same, so dividing by 1, and then divide by 9.8, x is going to be approximately 0.1 meters. That's how far that person can walk over the edge before the board tips over and they fall.
So that's from your pivot.
From the pivot point, measuring from that pivot point, which I put at the edge of the picture. Does that help with that?
So that's where it would pivot.
That's where we pivot around, yeah. You can put the pivot point anywhere. The torques have to balance around any pivot point. I just picked one because I need to know the distance from the edge of the board, so I picked that as the pivot point.
Okay, that's really helpful.
Okay.
Is that about, I mean, something like this, about the extent of the torque problem.
Yes, for an exam, yeah.
Okay, nothing that's gonna really involve a bunch of angular forces.
I can't really think of, I mean, that, surely a homework problem might involve angular forces, or you might have something addition. I put a box at the end, at this end that weighs 10 kilograms. How much further can I walk out? You know, it might be one additional torque you have to deal with that you would add to the torque of the board.
Right.
The box at the end would be 1.5 meters, whatever the force of gravity is, that you'd add to the board and then set that equal to the person. But that's as complex as I would get.
So really, you're comparing your clockwise to your counterclockwise torque.
Yes,
That's-
and if the counterclockwise torques win, who cares? Because it's balanced, it'll rest on the platform. If the clockwise torques win, it's going to tip over.
Right. Okay. Cool.
Right? Awesome. Okay. And moving on, we talk about torques and muscles. So basically, we've got more static stuff. Chapter 10 gets into rotational motion and angular momentum. So it goes back to angular motion, like we talked about with uniform circular motion, but starts to introduce, instead of just the kinematics, it starts talking about the dynamics. Like for instance, there is rotational kinetic energy, which is equal to 1/2 times the moment of inertia times the angular speed squared. There is angular momentum, which is moment of inertia times the angular speed. So there are equations that deal with the rotational analogs of, this would be linear kinetic energy and this would be linear momentum, right? The linear versions of those equations. The thing to note is, what is moment of inertia? I. Moment of inertia is how difficult is it to get an object to spin or to stop spinning once it's spinning. It's the rotational analog of mass, right? A bus has more mass, more inertial mass than a car. If a bus is out of gas, it takes a lot more work, right? It's a lot harder to push a bus to get moving, or if it's rolling, to stop it. For these pulleys or wheels that we had on the wall, right? This obviously has to deal with mass. It's similar, but it's how the mass is distributed. So I is equal to some constant, typically, times mr squared. If all the mass is at radius r, the moment of inertia is mr squared. For a sphere, if it's a solid sphere, it's 2/5 mr squared. For a hollow sphere, it's 3/5 mr squared. For a disk, it's 1/2 mr squared. For a ring, it's mr squared. It depends on the shape of the object. And the cheat sheet that I provided for you gives moment of inertia for basic, on the top of the second page, moment of inertia is for basic structures, solid sphere, hollow sphere, and so on. A simple example would be, think of a merry-go-round filled with all of your adult friends. If they all stand on the outside of the merry-go-round and you try to spin the merry-go-round, it's a lot harder to spin than if they all crowd at the center. It's a lot easier to spin. So even though they have the same mass, it's how that mass is distributed around the rotation point. The farther the mass gets from the rotation point, the harder it is to spin it around, or stop it once it's spinning. But moment of inertia has units of kilogram meter squared, always kilogram meter squared. This constant might change depending on how the mass is distributed. It can never be greater than mr squared. If all the mass is at radius r, then it's mr squared for a circular object.
Kilogram per meter squared.
Kilogram meter, not per,
Times.
kilogram meter
Okay.
squared. Yeah.
Okay, and then can you just repeat what you said below the potential rotation, what the L is?
Angular momentum, right? So linear momentum, P, depends on the mass of the object and the linear speed of the object. So the rotational analog of mass is moment of inertia. The rotational analog of velocity is angular velocity. So the moment of inertia, the linear momentum is m times v. The angular momentum is I times omega.
Got it. Thank you.
And angular momentum has to be conserved also. And that's when they did that really exciting experiment. If you saw the video of me holding the weights and pulling them in and spinning more rapidly. It's how divers, when they tuck, they rotate more quickly, and then when they stretch out, they rotate more slowly. Or in figure skaters, when they jump up, they pull their arms in to rotate quickly, and then they pull their arms out to rotate slowly. So how the mass is distributed, right? If you have the mass near the rotation axis, I gets smaller. If I get smaller, then the rotation speed has to increase. And again, you can even do this yourself on a merry-go-round or with friends on a merry-go-round. Have someone spin up a merry-go-round. You all are in the center of the merry-go-round spinning. When you all walk to the outside, the merry-go-round will slow down. And if you walk all back to the center, the merry-go-round will spin up again because of how the mass is distributed. So that's conservation of angular momentum. So it's the same as the conservation of linear momentum in collisions. It's just that for angular momentum, what'll change, as you change I, the omega will change. The angular speed will change. Does that make sense? So that was largely, and again, the book talks about how the rotational analogs of an object. So for a rolling object, like a tire, like a bike tire is both moving linearly, right? You're moving forward on a bike, unless you're riding a stationary bike, and the tire is spinning. So on a bike tire, you think about it, the bike tire has some forward speed, and it's also rotating. So the kinetic energy total of the bike tire is the kinetic energy for the translational motion, the linear motion, plus the kinetic energy for the rotational motion. So that's equal to 1/2 mass of the tire, speed of the tire squared, plus 1/2 I omega squared. So that's the total kinetic energy of the bike tire for rolling situation. So it's not just spinning on its axis, it's actually moving forward as well. And your book does talk about that a bit as well. So that was chapter 10. I'm not going to worry about gyroscopes on 10. Chapter 11 is fluids. So concept of density is introduced, and most of you have had a chemistry class, so density is not a new thing. But the density of an object given by the Greek letter rho, right, is the mass over whatever volume that object contains, assuming the object is uniform, right? So we have a constant density. Density is important when talking about fluids because it determines if an object sinks or floats. Then, when dealing with fluids, we have equations dealing with pressure. Pressure in SI units, it's just force per unit area, lowercase p, force per unit area, so it's newtons per meter squared. We call these pascals for pressure, PA, big P, small a. Pascal is a unit of pressure. So the bigger the force, the bigger the pressure, or the smaller the area for a given force, the bigger the pressure. When airlines started, making commercial airliners, for a plane, you want to make it out of strong, light materials because the heavier your plane is, the more fuel it takes to keep it in the air. So aluminum is used in a lot of construction. There was a time where women weren't allowed to wear stiletto-heeled shoes on airlines because you think of all of your weight on a little tiny heel that puts so much pressure that on these airlines, these decks made of thin aluminum, they'd actually punch holes in the airplane as they walked down. The old bed of nails trick, right? It's like, I'm going to lay on this bed of nails. Well, if you have a lot of nails, you have a big area, the individual pressure for a nail decreases. So regardless of your force that you put on it, your body weight, you're not going to really puncture your skin. You'll have little, pressure marks. A bed of nails doesn't work if there's one nail, right? If all that pressure is on that small area, that's going to go right through you. So that's pressure. And then we get into talking about how pressure changes.
With pressure, so I know that you said SI units as pascals. I know there's another unit that sometimes shows up. It's
Atmospheres.
Atmospheres, yeah. Are we gonna have to know the conversion for it, like apply the conversion just in
Yes.
case? Okay.
So basically, 1 atmosphere is,
760.
nope, that's torr. That's torr, is another one. 1 atmosphere, the conversion should be in the sheet I give you.
Yeah.
101.5 or 3
325.
kilopascals. Kilopascals. 101.3 kilopascals. If you just use 101, that's fine. So Pascal's principle, that's why we have a unit of force named after Pascal, because he did a lot of work in this area, states that the pressure is constant basically in a closed system. If you have a closed system, the pressure throughout that system remains the same. It's how you can squeeze on the bottom of a toothpaste tube and toothpaste comes out the top, right? So in an enclosed system, force per unit area is the same. Force 1 over area 1 equals force 2 over area 2. The neat thing is you can use that to your advantage. For example, if you have a hydraulic pump system. I don't know if any of you have ever had to change a car tire and use like one of those old school jacks, pump jacks. That's why they work. You put a small amount of force through a large distance on one end, pumping fluid, and out the other end, you get a large force that goes over a small area. So if you push down here with some force on some area, this larger area, A2, which is larger, will give you a smaller force. So it's sort of the opposite of what I just said from a fluid perspective. It's how your brakes work, right? How you can, if you have your brake pedal, you push down on your brake pedal, it goes through some inch or so of play. That small force over a larger area or distance gives you you end up pushing the brake pads, the rotors, I guess, against the brake pads over a small distance, applying a larger force. So just from think of it, cars not have power brakes, though they're assisted, of course. But the old school cars that just had hydraulic brakes, right? You'd be able to stop a 2,000-pound car with your toe, right? You just push on this brake, and the brake pads basically get pushed against. All the kinetic energy is lost to thermal energy and heat. So you can use hydraulics to give you mechanical advantages, just like a lever system, right? Where if you want to pry up a big boulder, put a little pivot point in, put a long, thick stick, you could push down a lot on this end, it moves a little bit on that end, lifting a larger force. So it's all mechanical advantage. So that's Pascal's principle. The difference between gauge pressure and atmospheric pressure got a lot of people. AUG. Gauge pressure is equal to whatever pressure you have minus the pressure of 1 atmosphere. So when you pump up your bike tires, and it says to pump them up to 50 psi, that's actually 50 psi above atmospheric pressure, which is 14 psi. Because when your bike tires are flat, they're actually not zero pressure in there, it's just regular air pressure, right? The pressure in your tires is no different than the pressure outside of your tires, which is why they just flop around. If they had zero pressure, they actually suck in. I don't know if anyone has shown a video of, I'll show one very quickly, of what happens if you actually lower the pressure of something. A second to bring this up. So air pressure around you is at 14 pounds per square inch. So for every square inch of your body, every square inch of the walls here is being pushed down by 14 pounds. But we're fortunately made of mostly fluid, it's incompressible, so we don't get pushed down to nothing. But our body has to accumulate to that pressure. Dramatic changes in pressure can cause problems in the body. Rapid decompression, if you go down, you're a scuba diver or a deep sea diver and you go down for a while, when you come up, you have to depressurize in stages. If you depressurize too quickly, the fats that are dissolved in your blood actually precipitate out. And rapid decompression can actually basically solidify the fats in your blood, and your blood just won't flow anymore. It just stops. If your body doesn't explode completely. So, to show you what I mean, how powerful atmospheric pressure is, this is a railway car. Usually hauls, natural gas at high pressure. All they did was pump the air out of it. That's all they did. That's just the weight of the atmosphere pushing it down. There's another one. That's crazy. So the gauge pressure inside that, when it's open and air is being sucked out, is 1 atmosphere. The gauge pressure is 0. But there is still 1 atmosphere of absolute pressure in there because it balances with the 1 atmosphere of pressure outside. When they tried to create 0 atmospheres of pressure inside, or -1 atmosphere gauge pressure, the outer atmosphere just shows you how powerful, how much weight your body is supporting the air above you. So this is a fun video. Then you have, let's put that down and go back to House physics. So if I give you something, I tell you the gauge pressure of something, you have to convert it to absolute pressure before you use it in any of these equations. Right? Ideal gas law equation or something like that. All you do is add an atmosphere to it, or add a 101.3 kilopascals. So I tell you what the pressure is. The gauge pressure is 3 atmospheres. That means the absolute pressure is 4. Yeah.
Would it be possible to do an example, because it's hard to just conceptualize it
Sure.
as we're talking about it?
There was actually a test example or homework example very recently where it was asked, I think it was due on Wednesdays, where the gauge pressure, AU, let's say was 1.5 atmospheres. Temperature went from 23 degrees Celsius to, let's say, minus 10 degrees Celsius. What is the new gauge pressure? Assuming constant volume, constant number of particles, right? Well, that's ideal gas law. Pp equals nRT 1 over P2 V2 equals N2 RT2. Assuming no particles escape, assuming constant volume, ideal gas law cancels, you have P1 over P2 is equal to T1 over T2. We're solving for P2, pressure 2 is equal to T1, oh sorry, bring that up here, so it's T2 times P1 over T1. Right, so to solve this, a couple of things. One, everything has to be SI. So what are the temperatures that we use? Kelvin, so we have to convert. So T1 is 23 degrees Celsius, so we add that to 273.15 to get 296.15, so 296.15 Kelvin for temperature 1. We're taking 273.15 minus 10, so 263.15 0.15 Kelvin for temperature 2. And then the pressure has to be SI, but it also has to be absolute pressure. So this is gauge pressure. So P1 is actually equal to 2.5 atmospheres for absolute pressure, and then you multiply that by 101.3 times 10 to the 3 pascals over 1 atmosphere. Atmospheres will cancel. Do I have a calculator on me? So 101, actually I just, like 2.5 atmospheres, my calculator will just convert it. 253312. 253312.5 pascals. So multiplying this by that ratio of temperatures, 296.15 divided by 263.15, I get pressure is 285,079 pascals. But that is absolute pressure. So to get gauge pressure, we have to subtract an atmosphere, or subtract 101,300 pascals. Minus 1 atmosphere. So the real final answer would be 1.8 times 10 to the 5th pascals. So a lot of conversion in this problem. A fairly simple relationship, P1 or P2 is T1 or T2, but we had to convert temperatures into Kelvin, and we had to convert pressures into absolute pressures. Yeah.
So if you were adding the atmosphere for the P1 there, but then you were still taking off at the end.
No, because you're calculating a ratio. Because of this.
Got it. Okay.
So sadly, you can't just say, well, I'm doing gauge pressure on both. Sadly, no. And one way to see it easily, let's say the gauge pressure was 0. Because it could be 0 atmospheres, right? That means the absolute pressure is 1 atmosphere. So I put 0 in here, but I change the temperature, I'll still get 0 out there. And that's not the right answer, because the pressure is still actually 1 atmosphere. So it would change. If you put 101.3 kilopascals in here, with this ratio, you'll get a different pressure out. And that pressure would, depending on how the temperature changed, might be below 1 atmosphere, or so the gauge pressure would actually be negative. So you have to have absolute pressures. But that's an excellent question. Does that make sense? Other questions on this? All right, so Archimedes' principle talks about how buoyant force the buoyant force on an object, so when you submerge an object, or an object is floating, the buoyant force equals the weight of the displaced fluid. So if you know how much fluid is displaced, I have Kleenex up here if you need. If you know how the volume of fluid that's displaced, you know the density of the fluid, you can calculate the mass of the fluid. If you know the mass of the fluid, multiply it by 9.8 to get the weight of the fluid. That will tell you what the buoyant force is. So that's how ships work, right? Container ships. They're big and wide. Metal doesn't normally float. But if you make your container ship really, really wide, so it displaces a lot of water, then it will have a very large buoyant force holding itself up against gravity. So ships, are hollow on the inside, mainly, right? That's in lower decks and things like that. And they just need to displace the water in order to float. If they don't displace enough water, they don't float. That's up in the Titanic, right? Water started getting in, it wasn't displacing that water anymore, and it sunk. So for objects that are submerged, it's the full volume of the object that gives you the buoyant force. For objects that are floating, it's just the displaced, it's the volume of the displaced fluid. So not the whole object isn't displacing the fluid. So if you think of a styrofoam cube lightly floating on the ocean, the reason it floats is because it doesn't have to displace a lot of water to get a high enough buoyant force to fight gravity. Not worry about capillary action. Again, that's a very specific application for the students who are taking this for health science reasons, which are most of you, but. And then fluid dynamics, 12 we talked about earlier. So, any other questions before I let you go? Thanks for sticking around. I hope this is helpful. Super helpful.
Definitely, yeah. Especially working through some problems.
Okay, awesome. But remember also that I have all of those problems I worked out from the book, the videos. So if there's any chapter that you're uncertain about, you can jump to those, and I talk through the problems. It's YouTube, so you could probably accelerate me and listen to me at learn 1.5 times faster. There was that great, I remember this great YouTube comment, what was it, I think Ken M did it, where it was a YouTube video, how to learn 10 times faster. And you commented, and I watched this at 1.5 speed, so now I learned 15 times faster.
Aaron, the one question I had is you mentioned earlier in the video, you talked about how you can use your calculator if you have a quadratic equation like to solve for t.
Yep.
Is there any way that you could show me how to do that? Because I had to do everything.
That, unfortunately, it depends on your calculator. So what I strongly recommend doing is,
This one.
but if different TIs do different things. So
Yeah.
what I would recommend doing is just Googling quadratic solver for TI, whatever you have.
Got it.
And it will either show you, if it's intrinsically put in there, it will show you how to access it, or it will show you how to write a short program to do it.
Okay.
You can download them a lot of times too.
Yeah, with them, I forget the new ones actually connect to your computers. We had, when I had the TI-81, we were plugging everything in. But yeah, you can download or write a very quick program to do that quadratic solver. So I recommend doing that tonight, and then just working out a few, just basic quadratic equations, just to test it. So if you have, I know that the 89s and things like that have built-in solvers. 83s and 84s. 84s might have it. I don't know if the 83s do. But you definitely Google quadratic solver TI-80, whatever you have, and you'll get videos or helpful tips on how to do it.
Got it.
Sometimes I have an issue with, you know how we had to change the rad?
Oh yeah,
mode
degrees to rad, yeah.
So it's always supposed to be on degrees, not rads, unless we're doing.
Unless you're doing something very, just keep it in degrees. That's the safe way to do it. So when you do inverse tangent, inverse sine, inverse cosine, you get those angles out in degrees. Now, we were talking about how theta is in radians per second for like angular motion stuff, but that's still algebraic. You're not doing sines, cosines, and tangents with those. So it should always be in degrees.
Because if I change it to rads, I noticed sometimes when I was changing it, and then I would start working on a different problem, and I would get it wrong, and it was because of that.
Yep. If you're using any of the trigonometric functions, a sine, cosine, or tangent, and you have it in radian mode, you will get the wrong answer.
I did that in Excel yesterday.
Oh yeah, because Excel assumes everything is radians. Yeah.
So you had to convert to degrees.
You gotta multiply 180 over pi for everything. Yeah, it's a pain in the butt. I wish Excel had I wish it had like and maybe even does now, but just like a cosine underscore d for if it's a degree or something like that. But
Or a setting that you could give it to.
Wasn't there like one section, I think it was like the chapter 6 stuff where it said like it's better to put it into radians though? I don't remember like what it was for. I just remember I wrote in there like make sure you're calculating.
well, oh boy, I don't recall what that would be specifically. I do know that when you're like calculating like rotations per minute, you definitely want to do the conversion to radians per second. But all the angles. Oh, sorry. Small angle formula. When dealing with, there was an equation where for pendulums, where the author just gave you theta. If you ever see an equation with just theta in it, it has to be radians.
with delta S.
Well, yeah, that's the radius of curvature. Theta is always measured in radians, but whenever you use it in an equation, if you see something like, I'm just going to make up something up, like h times t divided by theta, theta has to be in radians.
Okay.
If it's sine theta, then you can use, of course, degrees. But if you just see theta by itself, it has to be radians. But again, you only really worry about errors in degrees and radians when you're trying to do those usually trigonometric or inverse trigonometric functions. That's when it's important to say, oh, am I plugging this, do I want degrees out of this inverse sine, or am I putting sine in degrees? Then you want to be in degree mode. If you're putting it in radians, you want to be in radian mode. You just have to be aware of which version you're in.
Yeah.
Right, I'm going to stop this.